we've covered so far, where we go from here, and maybe start with the Einstein field equations and from there work backwards. Okay? So just for a quick recap, I'll tell you the problems that we have coming from special relativity to general relativity. And I'll show you the different players so that you're not confused and you understand why we're doing these things. Yeah. Okay. Could you confirm? Can you still see my screen?
Yep.
Okay. So I want to start off by just taking.
Chinmay, sorry to interrupt, but there's something wrong with your voice. Like you sound really wonky. Yeah.
It's quite muffled.
It's
Yeah,
muffled. Still bad? Or is it better?
Better.
I think it's better.
Much better.
Okay. So I want to take a step back today. Stop me if you think my voice is still muffled. Okay. I'm going to write down the Einstein field equations. And I'm just going to introduce you to the different players that we have. Okay. Can everyone see what I've written down? You just have to stop me in case you can't see.
I don't see anything.
Yeah, it's completely blank.
Yeah, it's completely blank.
Okay, we just have to work out the sync. There we go.
Yeah, it's working.
It works out.
Okay, so this is an equation, hopefully by now in the course, some of you have seen before. And I want you to start thinking about the quantities that we have on both sides. And this is just a friendly step back from what we've been doing so far. Okay, so the right-hand side of this equation has this thing here, which is the energy momentum tensor. Okay, we have a tensor on the right-hand side. And on the left-hand side, we have another tensor called the Einstein tensor. Okay, so can everyone see, or is it?
I can just see it's taking quite some time to sync.
Okay, we'll fix this. Okay, we'll walk through this. Okay, so you might have seen before that Einstein's equations relate the curvature of spacetime to matter content. You have the information on matter, it curves space, and the curvature of space is what we call gravity. There's no force per se, right? So I just wanted to tell you the different things to solve and goals for GR before going ahead and continuing with left off last night. So if you look at the left-hand side, this thing that I've called the Einstein tensor, okay, you need to be thinking of this thing as containing all of the information about a curvature. Okay, all of the information on the left-hand side contains curvature. So, so far, right, the player that we've worked with.
It's a little muffled again. Wanted to understand. Yeah.
Okay, is this better?
Yeah.
Okay. So you guys remember we worked out this quantity before. We've seen a bit of this before, the metric tensor, right? And if you remember the last lecture, we spoke about things called the outer products. And we discussed understanding tensors through what we call the goal for the day, and the reason that the Einstein field equations are difficult to solve is because these are coupled differential equations. So it's not that we have G mu nu to start with, and then from here we build up to the equation. It's the opposite. We start with these field equations, and by making various assumptions for it, the solution to an Einstein field equation gives you a particular metric. Okay, everyone, I want you to understand that the goal of working with the field equations is the only time you'll need them is to get this, G mu nu. Okay, so if you're a physicist, you say, I'm going to let other people work out how we solve this. And if someone hands you this thing called G mu nu, from this you start to make important, calculations. So once you have a G mu nu, this tells you many, many interesting things. From this G mu nu, you can work out, for example, the frequency of light. And we can learn how to do that. You can work out the various effects of, so in GR, unlike we had, so we don't have a gravitational force. Okay, remember, we have a curvature of space-time. And in GR, particles do not move in straight lines. There's no concept of a straight line. But if you remember the discussion we had on manifolds, you have a curve on your manifold. And the path that these particles take on these manifolds is called a geodesic. Right? You'd have heard this before. So this is an important thing. And this geodesic is something you can calculate from the metric. And it's actually something that we've seen before. We've seen this before. If I told you if you can calculate the length, it's the integral of this separation vector. Do you remember this from the previous lectures? Right? It's this thing which I told you can write this in terms of there's a square root, there's a G mu nu, and you have two tangent vectors. And you have a particular parameter, which if this thing here is 1, is called the affine parameter. Do you remember that? This is what we covered last time. So if you're looking at understanding paths and lengths, you can do that only when you have a metric. Okay, so that's why metrics are important. The third thing you can do with the metric is understand, equations of motion. And there's another way you can equivalently calculate the geodesic, and that's through the Euler-Lagrange equations. And that's something we saw in the variation calculus lecture. Okay, there's an equivalent formalism between the two. You can calculate geodesic through this way as well with a metric. If anyone types in the chat, just read out what the question is, because otherwise it's going to be difficult for me to answer what this is. Okay, so what I wanted to do today is to say that G mu nu is our end point. Okay, this is where our fun begins once you have a G mu nu. So there are various different applications of GR that you might have seen, and all of those have a unique solution to the Einstein theorem. So one particular solution is the vacuum solution, which is Minkowski space. Okay. The second possible one that you could have is Schwarzschild, the black hole. I keep forgetting how to spell this. The third one is when you have a rotating black hole called the Kerr. Then you have various other conditions. You have the de Sitter. You have something called Milne. You have, then in cosmology, if you're working in cosmology, there's something called the Friedmann-Robertson-Walker metric. So these are the interesting ones. If you leave aside GR and you work through other different fields, you have more interesting metrics. Like in quantum field theory, you have many other kinds of metrics. There's something called the Kahler metric. You have, in QFT, you have the Euclidean one, which is important. Okay, so just remember that the goal of learning Einstein's field equations is to arrive at one particular new value of G mu nu. Once you have a G mu nu, or if someone gives G mu nu, you can use that in your research. You want to calculate the redshift around the black hole, you want to calculate gravitational lensing, you want to work out how gravitational waves work. All of that comes from a particular solution of G mu nu. Okay? So that's what I wanted to tell you today, that I just wanted to explain, when you look at the field equations, I wanted you to understand what these various quantities are, how they are built, and how we arrive at them. Okay, so I'm just going to erase a bit of this and tell you how we build this up. Okay, so in physics, remember what we tried to do is to reduce our notational, make it neat. So this G mu nu that you see on the left is actually it's made out of a larger curvature in GR is something called the Riemann Tensor. I don't know if you've heard of this yet, but this Riemann Tensor is something that we use to describe curvature. We didn't discuss that today. So what I wanted to say was that if we have G mu nu, okay, this big, you have a capital G, this is the Einstein tensor. If you have a small one, that's the space-time metric.
My voice now and then it's like normal and then it's
muffled. Okay.
Yeah.
Strange. Sorry, there's like renovation work in my room, so I had to hang on. See if I can change this. Okay.
Try speaking now, maybe.
Is this better?
Yeah. It's good.
Okay. So we have G mu nu, which is the Einstein metric, the Einstein Tensor, and we have this small one, which is our space-time metric, right? Even if you remember our previous discussions, this thing tells us about distances. It's a map that tells you how to raise and lower. Yeah. So there's a relation between these two, and you'll see why solving this Einstein equation is difficult. Okay, so I'm just going to give you, I'm going to tell you how we do this. So today, I want to start off with this particular thing, that if you remember our manifold discussion earlier, right? If you had a manifold like this and you had a curve running, I told you that at each point that you have a particular tangent space to this curve. And the problem in GR is that two different points on your manifold in general have two different metrics. Meaning, in this particular region that we have here, you have one particular G mu nu, and in this region, there could be another G mu nu, something else. It's not the same. So when we work, this is the reason that it's incredibly complicated. And if you wanted to pursue a career or do a research project, this is where you need numerical relativity, for example. It's incredibly complicated because you have to take simplified assumptions often that whatever the space is, maybe in this entire manifold, you can say, well, the metric is the same across this. There's another complication as well. If you're studying cosmology, for example, the problem is that this G mu nu isn't just varying with respect to where you are, but also it changes with time. Tell me if my voice is muffled. Okay. So in cosmology, the problem is that this G mu nu changes with time. But in the universe, your space-time metric is going to be vastly different from your late universe space-time metric. So this is an area that we want to be looking at. Okay, so do you remember we said that we have these tangent spaces, right? We have tangent spaces that are connected to every point. And if you remember what I told you earlier, the smart trick was to assume that any point has a neighborhood which is locally flat, or locally around a point, it behaves like Minkowski, right? But globally, that can't be said. So we need a way to connect vectors that are here living in this tangent space with vectors that are living in this tangent space. If anyone has questions, I can hear like typing going on in the chat, but I can't go and read it. I think it gets muffled if I do that. So just give me a shout if you. It's getting.
There's
It's
no question. Yeah, it is getting muffled. That's the issue. Like periodically, it's not like it's unpredictable.
Strange. I've always spoken like this. Okay. Hang on. Let me try getting a pair of headphones and seeing if that works. Shall we take a 5-minute break then? I'll just get that and come back.
Sure.
Okay, sure.
Yeah.
No problem.
Can you hear me now? Is this better?
Yeah, it's better, but the voice when it gets muffled in between or periodically. So maybe if there is any muffling, we'll okay left.
Could someone say something?
Yes, your voice is fine.
I hear you. Let me
Am I
reset
audible?
my.
Yes.
Okay, can we test?
You're audible, Chinmaya.
Strange. Very strange. Okay, could Apurva try saying something?
So am I audible?
Yes. Okay, great. Can you
Okay.
hear me?
Okay, you try speaking because your voice was normal in the beginning, but now
It's muffled now.
no, it's fine. It's fine now. It's fine.
Okay. Okay, I'm not sure I know how to read your name. Is it Ilfons? Okay, we spoke about this in the previous lecture. The Alphonse. Okay. So the problem is that in GR, when we work with flat space, it's well behaved and we know how to work with it. But in general, curved spaces can be incredibly complicated to deal with. So the assumption that we make in GR, which is mathematically very elegant and is the only thing that allows us to discuss things like continuity and calculus itself, is that we say that locally, wherever we are, the world looks flat. And the picture that I want all of you to think about, and we're going to do this again, is that if you have a circle, it looks curved, right? But if you were an ant standing on the top of this circle, to you, it would look almost flat, just the top, just the area around you, which is to say that we don't talk about it globally, but we just only look in the small neighborhood around you, and we say that that local neighborhood that you have, mathematically, the statement that it's isomorphic to RD, meaning that this neighborhood here is isomorphic. I think the word is that is RD. Or if we're working with Minkowski, we'd say that it's isomorphic to Minkowski.
Chinmay, sorry to interrupt, but your screen is not visible.
My screen isn't visible.
Yep.
Right. Okay, I forgot to share my. Good point. Okay, but my voice is okay now?
Yeah, it's fine now.
Yeah, way better.
Okay, good. Right. OneNote. You should see my screen now. Yeah?
Yeah.
Okay, so yeah, that's the point. Okay, so what I wanted to say was that if we understand what these quantities are on the left and right hand side of the Einstein field equations, that's all we need to do to work out GR. So the left hand side, this G mu nu here, is built out of this metric. Okay, it's built out of this. And the right hand side contains all of your information on matter. So I want to talk to you about how we go from our space-time metric to describing curvature, because that's a big leap conceptually, right? Our space-time metric only tells us distances between neighboring points on our metric, a manifold, sorry, right? We said we have various tangent spaces. And the metric just gives us, in our infinitesimal separation here, between here and here, it helps us relate our basis vectors. If everyone remembers our relation, we said G mu nu is defined as this thing here. Does everyone remember? So it's a relation between the basis vectors, but it holds for any set of basis vectors. Okay, so what I wanted to talk to you about today was that if you have a manifold, and if you remember our curve, at any point that you have a tangent space, and at another curve, you have another tangent space. So the problem is that any one vector that's here does not live in the tangent space. Sorry, how do I undo? Yeah, any vector that we have here does not live in the other tangent space. So there's no way we can connect and talk about things like velocity. We can't, because any tangent vector that's here does not live in the one that's here. So we need a way to compare a vector that's in this space with the one that's living there. And that's how we do calculus. And that's the problem that we have in GR right now. So to give you an understanding and an idea for why this isn't just simple, because if you remember calculus, the goal was we had a grid, a nice flat grid, which I've drawn terribly. And if you had a vector that was pointing this way, you could move this vector along and it would still have the same length and the same orientation, right? None of that has changed. But the problem in GR is if you move along your manifold, this vector that had this particular orientation might here only be like this. It could be pointing in a completely different line. And the example I want to tell you and ask you to think about is that if I was to ask you to stand in your room right now and only face forwards, like face in one particular direction, right? So imagine just to do this exercise in your head. So if I ask you to take a step forward, I ask you to take a step right, I ask you to take a step back, and then all the way back to the left while facing the same direction, you'd always be pointing the same direction, right? The direction that you're facing never changes. That's the equivalent of us moving around a vector in flat space, right? So if I asked you to move around in your room and you were pointing here, you go forward 2 steps, you're still there. I ask you to go right 2 steps, you're still there. I ask you to go back, you're still there. But the idea is that if I asked you to point in a certain way on the Earth, and let's say you started at the North Pole, okay, and I ask you to point in a certain way, and I ask you to walk down to the equator, okay, and I ask you to just go left, 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 left. And then when you come back, you'll notice that the direction that you're pointing in is not the same anymore. And that's a feature of curved space that we don't have in flat space. And that's a direct, consequence of having vectors in different tangent spaces. And what this means is that depending on the path that I take to compare a vector that's here, let's say I compare a vector that's here to a vector that's living here, the path that I take is extremely important because if I take 2 different paths, I might end up with 2 different vectors. And the way to think about this is, let me scroll down. So if I picture that as one path, picture this as one other path. You might have, like your vector as you move it along, might face this way. Right? But the same vector, if you took it this way, you might find that in doing so, it's pointed in a completely different direction. It's the same vector, but just here, depending on the path that you've taken, it faces a completely different direction. This is the problem with GR, and this is the problem with us doing any kind of calculus and understanding any kind of equations of motion, because the path that we take around our manifold is as important as the vector itself. So we need a method for us to do it, some sort of standardized way and a way to understand curvature. Okay, and this method is something known as parallel transport. And I'm just going to give you the basic idea to this. And the idea essentially is that if you want to take a derivative, right, so remember our notation for anyone who's joined us for the first time. We have 4 coordinates that we work with. Okay, and instead of me always writing d by dt or d by dx, okay, I'm going to substitute this by using our 4 vector notation, saying that x mu equals this. And if I substitute 0, 1, 2, and 3, I get these values, right? So now if I talk about a derivative, like d by dx1, this means I'm just talking about d by dx. So I can take a 4 derivative by just writing d by dx mu. And depending on my value of mu, whatever value this is, it tells me what derivative I'm taking. Okay, so the idea is in GR, anytime we take a derivative, okay, we're going to write this as this. Yeah, we have to add some term, okay, a term in addition to this, which compensates for our vector moving along different paths. Okay, and so this is a very special derivative that you have in GR, and this derivative is known as the covariant derivative. And this is how we do calculus on curved spaces. So have any of you seen covariant derivatives before? Is this the first time you've all seen them? If it's the case, the way we do this is it's simple. Okay, so in GR, the intuition behind this is as follows, right? Like we need a way to compare the two. And we need to take a derivative from one tangent space to the other while trying to keep our vector moving parallelly. Okay, so that concept is known as parallel transport, and we're going to do that today. Okay, so when we do any kind of derivative in GR, okay, whatever kind of physics that you're working with, the difference between flat space, okay, is that we can take our usual derivatives. I'm going to write that as d mu. Okay, this thing is just this. If anyone has any questions about what this quantity is, give me a shout. But I'm hoping by now we've all become familiar with it and we've worked through the different equations. So in flat space, you can just take derivatives. You can work with your usual familiar operators like the Laplacian. You can work with all of those. The problem in GR is that it's path dependent, which means you need to add an additional term to this derivative. Okay, and this additional term that you add is something called the connection. Okay, so that's what we're going to work out today. So I'm going to talk to you about the connection, and I'm going to explain to you what we're going to do with it. So the way so remember, our goal at the end of the day is to understand what the Einstein tensor is. Okay, and I'm just going to break up and show you, maybe you can write this down in a separate piece of paper so that you understand where we are in the hierarchy or ladder of concepts that we're working on. So we want the Einstein tensor G mu nu. Okay, this Einstein tensor G mu nu is related to something called the Riemann tensor. The Riemann tensor is a tensor which has a lot of information about the curvature of your space. This Riemann tensor itself is built out of things called the connection. Okay, this connection that I just spoke to you about is what comprises our curvature. It contains all the information that we have about the curvature itself. Okay, so this connection is what determines the Riemann tensor. Okay, and this connection itself is made out of your space-time metric. I'm just going to write metric. Okay, so does everyone see why the Einstein equations are difficult to solve? So we start, if this is our solution, okay, and this is what we want at the end of the day, it's very difficult to get here because you have a lot of partial derivatives and other set of complicated stuff between your field equations, which are at the top, and our metric itself. And this is the reason that solving them is almost impossible. You need to work with strict assumptions and often use something called perturbation theory. And that's something I'll talk to you about because it's related to gravitational waves. So I just wanted to introduce the players that we have here, right? So we're going to have our metric tensor here. Okay, with this metric tensor, we're going to introduce a new derivative. This new derivative that I've written out here is called the covariant derivative. And it has the same symbol as the Laplacian. Okay, so in GR, this is your derivative symbol. So if you're ever doing GR, it's almost like a mechanical procedure that if in flat space you just had your normal derivatives, you just replace them with your covariant derivatives in GR. Okay, that's how it works. So we have this thing called the covariant derivative. So I'm just going to write this out so that no one is scared or no one's wondering where we're going with all of this. And I'm going to talk to you about how we define it. Okay, so we have the covariant derivative. And once you have this covariant derivative, you can define something called the connection. And the connection will have this symbol. Okay, this is something called the Christoffel symbol. And once you have this Christoffel symbol, with this you can build what's called the Riemann tensor. Okay, it doesn't matter where the four indices are, but there's this. This thing here, okay, the Riemann tensor, has a lot of information, a ton of information in it. So if I had to, let's take Apurva, okay? Apurva, can you tell me how many different equations I would have if I have this quantity out here? How many indices do you see?
Okay, is it like 1, 2, 3, 4, 4 free indices?
Yeah, so if our dimension is 4, mu runs from 1, 2, and 3. Nu runs from 1, 2, 3. Lambda is 1, 2, 3. Rho is... Okay, so how many equations do you see here?
256 maybe?
Exactly. Do you start to see why GR is a pain? This curvature tensor that we have has 256 equations needed to define it completely. So it's often useful. People have worked out that there are important bits of it and redundant pieces of information that can be separated. And this curvature has a lot to do not just with the surface, so how curved it is, but often has to do with scaling as well. Like, yeah. So they often divide this Riemann curvature into two kinds. There's something called the Vial curvature tensor and the Richie tensor. Okay, there's just separate parts of it. Like you can say if this Riemann tensor is this huge thing, you could say it's divided. Like this particular one is the Vial tensor, this particular one.
Yeah, scroll down a little bit.
Yeah, there you go. Okay, so I'm just trying to say that if we have this large bit of 256 equations, we don't have to use all of it. Like they all describe different kinds of curvature. And in Einstein's equations, we assume that whatever object that you have, okay, whatever size it is, we're going to say it's not going to be squashed anymore. Like, and this has to do with saying that a Weyl curvature is not particularly relevant. Okay, so we'll get to this later, but this is just a aside to tell you that this Riemann curvature contains so much information. We try to sort that out to take what's important and useful for our calculations, and we often find that unless you're working with very specific theories, you only have what's called this Weyl curvature doesn't become important. It's only the Richie curvature that's important. Okay, and there's a way to construct this. So I'm going to say from this huge thing that we have so far, this Riemann tensor, from here we're just going to end up with what's the same R. Okay, and this thing is the Richie tensor. Okay, so can everyone see the flow chart? So once you have this Richie tensor, G mu nu is actually defined in terms of the Richie tensor. It's something like R mu nu. And if I have a tensor, right? What if I contract this Richie tensor with the metric itself? So what do you think something like this gives me? So I'm raising, but can you see both indices are repeated? Okay, this I can write as R mu mu. It means I'm taking the trace of it. I'm just going to sum over all the diagonal elements. So this would just be R00 plus R11 plus R22 plus R33, right? So this quantity here, if I contract it, remember we started by saying that we can contract and raise and lower indices. If my upper index and my lower index are equal, this is akin to taking the trace. And this thing becomes a scalar. Why? Because you're taking components and adding them. So there's no vector anymore. It's just a number. So if you do this, remember it's 0, 0 plus 1, 1 plus 2, 2 plus 3, 3. This thing is called the Richie scalar. And the Einstein tensor G mu nu is just written in terms of this. I might be missing a couple of numerical factors, but it's unimportant. Okay. So now hopefully when you see this, you'll say, okay, I think I know the pieces that we have. G mu nu is our big actual equation, the big tensor that we have. You may also have seen the Einstein equation written like this, where you have this quantity here, but this is just simplified to the Einstein tensor. Okay, so R comes from this thing, the curvature tensor, the Riemann curve is the big one, right? That's where we get R mu nu from. R we get it from taking the trace of it. This big thing we get from G mu nu in a pretty complicated way. Okay, so does everyone see the flow chart? Like if you understand these players, you understand GR and you can perform calculations. Okay, so I've not told you where they've come from. I've not told you how to calculate them, but I've just shown you where we're going so that when we work out the lecture and we work out various other problems, you don't say, okay, wait, what is this quantity about? And if you're confused about anything, these are the things you want to be searching for. These are the players. Okay, so if you look at the list that we start with the metric, we have the covariant derivative, right? Then with understanding how our derivative changes, we get something called the Christoffel symbol. The Christoffel symbol tells us how to connect tangent spaces. With that, we build this enormous thing called the Riemann tensor, which contains all the information about curvature. And from there, we extract only the relevant terms for gravity, and we end up with what's called the Einstein tensor. Okay, these are our players in the curvature side of it. In the other side of things, you have the matter content, which is the T mu nu on the right-hand side of the equation. This T mu nu is called the energy momentum tensor. The good part about learning tensors, and so I hope this isn't scary to you, but the good part of learning 4-vector vectors and tensors and all is that there aren't that many, right? Like if you're learning about relativity, I can't name more than 5 or 6 that are important. Like if you understand what this is, you'll see it in every subject that you're working on from now. If you're working with fluid mechanics, relativistically, you'll see it. If you're working in cosmology, you will see it, because this thing here, while the curvature tensor talks about the curvature and the geometry of space, the energy momentum tensor talks about matter content. Okay, so what do you expect this to be? This T mu nu, again, can someone tell me how many equations we have? You see 2 indices. How many equations do we have?
4.
4. Any other answers?
16 equations, right?
16. It's not 4. So mu can be 4. Mu can also be 4. So it's 4 into 4. It's important to notice because when you have an equation like this, for example, you have g mu nu equals 8 pi g over 3 t mu nu, you actually have 16 equations. Okay? These are actually 16. So it's important to know how many we're working with at all points in time. So this works out to be our matter content. And a trick that I want to tell all of you people when you're working with GR, okay, whether you see something like G mu nu, whether you see something like T mu nu, or any sort of metric, anything, a tensor with any sort of indices, always separate it out into the following components. Like ask yourself, so something like this, G00, some people like thinking in terms of numbers, some people like thinking in terms of coordinates. So G00 is same as the time component of our metric tensor, which, if you remember, Minkowski space was -1, right? What I'd ask you to do is anytime you have a tensor, separate out the following 3 things. So this is the time component, okay? Time. Then you have something called the mixed component, where one is time, the other is space. And if this is confusing to you, mu, remember, takes the value 0, 1, 2, 3. And because there's only one time and the rest are space, okay, you treat the 0 component to be time, and I, which can take the values 1, 2, and 3, is the spatial component. So always when you're working with anything, GR, QFT, this is a very useful trick that we will do again and again and again. That often the time component is something important. This is the mixed component, okay? And Gij is the spatial part. You may have already seen an example of this in the first set of problems I'd given you, where I'd asked you to talk about the identity transformation. And did you notice how if you separate eta mu nu, and you say, well, I don't care about the 0 component, right? I only care about Ij. This is essentially just the Kronecker delta. Or in other words, which is to say that if I only look at this bit, it's an identity matrix. Do you guys remember that? It's the same trick that we're going to be doing again and again and again. So if you had to separate this out, okay, you ask yourselves what each means, and you'll find that the time component often is special. Whether you're working with GR or GR or classical field theory, electromagnetism, whatever. Okay, so here, the energy momentum tensor has the matter content in it. And the 0 component, okay, has to deal with the energy density. The 0I component has to do, I think, with flux. And Ij has to do with stress. It's called the stress tensor. And you can think of this just like if T mu nu was this large matrix that we had here. This particular component alone talks about the energy density, and you can take that for granted, right? Wherever you have this thing here is the stress, and the components along this side deal with flux. Okay, so hopefully you've now seen that the Einstein field equations really have very few limited players. You just have, this is something that's important. This is all the hard part here, okay? This bit, that's all the difficult bits. And once you have this, calculating the energy momentum tensor is fairly easy. You actually, in GR and in cosmology and all of that, we work with thermodynamics, a little bit of it, and we use the equation of state, which relates our energy density to pressure, if you remember. And we'll get back to this later. So does anyone have any questions about what we're trying to do with GR? Because I'm hoping this should give you an overview of the stuff we've spoken about. And if I go back a little bit, right, we've spent a lot of time determining what tensors are. So it shouldn't be scary. Like even if these things are called tensors, it shouldn't be scary because you've seen the outer product so far. And we've spoken about what the metric is, which is our fundamental quantity of GR. It tells us about distances, right? It helps us compare events. All of this stuff, right, is stuff we have to learn. But it's not scary because this thing tells us how to find derivatives. This thing helps us understand how tangent spaces are connected, the links, okay, to each other. The Riemann tensor, the Riemann curvature tensor has all the information contained in it, and you do not want to be calculating this thing. You need Mathematica. I think if any of you can calculate 256 equations on your own, good luck, right? And then you simplify that further and you get the Einstein tensor. So that's all GR is about. It's not scary. What I wanted to say is that if I had to list down the various players that we had, I think Mukund had asked me this question on WhatsApp, like how do different assumptions lead to different solutions of the Einstein equation? One of you had asked me that.
Well, that's Yuvraj, I guess.
Yuvraj had asked. Okay, so you'll find that there are very specific, what do you say? Every assumption that you take changes these quantities in some way. Like these are all the players that we have. Okay, so if you, for example, there might be any assumption that you make might simplify what this Christoffel symbol is. Another assumption, like I told you, we're throwing out the Vial curvature tensor, means you can simplify this thing here. Okay. When you're doing GR, you'll find that there are other derivatives that you might want to think about. Like, for example, in classical physics, you might have wanted to only take a derivative along a curve, right? This covariant derivative doesn't help you there. You'll need to find something else. That something else, I think, is called the intrinsic derivative. And it's related to this, meaning that we're going to get to that today. So does anyone have any questions about what this is? Because I'm hoping this gives you an overview of what GR is about. And I want to show you gravitational waves also for a second and tell you why it's extremely tough to calculate these things. So if, and then we move on to calculating the Christoffel symbols and actually defining them. And I'm hoping by the end of today, we can spend time on one or two solutions, maybe the first black hole for you guys. So if you've seen any sort of gravitational wave physics, okay, there are two aspects to it. The first is that you can talk about the source. Like, how is it produced? Okay, that's the first bit of gravitational wave physics. The second is how does it feel when it passes through you? So how is it received? Okay, and this bit here is where most people do these are both big problems in physics. Like here they talk about mergers of binary stars. There are important theorems that say you need two objects, like no spherically, like one single object spinning around and around will not produce gravitational waves. Like this is actually, there's a theorem that proves this. So this is an area of physics that's interesting. If you want to look at how gravitational waves feel, the reason that numerically this is difficult is, remember, we need to work out the curvature tensor you work in reverse for gravitational waves. You say that if this is my nice metric, flat space, okay, it's like this, nice and flat. For gravitational wave physics, you say we're going to disturb this. And when the gravitational wave comes to you, it'll look almost straight, but there's a tiny, tiny perturbation. So it's almost straight, but it looks like that. And how do you model this mathematically? You say, well, if this thing here is eta mu nu, okay, to my eta mu nu, I'm adding something. I'm going to add a small quantity, and in literature it's called h. And this h is just something tiny, like much lesser than 1. So this is how we do gravitational wave physics. So you take this new quantity here, okay, this sum total, and you call this your new metric. And I'm going to call it G. Okay. And from this new metric, G mu nu, you work backwards again. Like you start to create your Christoffel symbols. From the Christoffel symbols, you start to calculate your curvature tensor. From the curvature tensor, you can work towards the Einstein equations. And from there, calculate the energy momentum tensor. You can calculate the light, the frequency of light. You can work out various different quantities. You can work out predictions for how they look and work out solutions. So that's what this is about. Okay, so if you were working with this, you'd see why this is particularly challenging. It's because these are coupled differential equations. So how one changes affects how the other does. And so this is usually worked out numerically. Like you work with computers, you say, okay, we'll take it to this, and then you iteratively try and get better and better results. So that's how this works. Okay, so I'm going to move back now towards the covariant derivative. Any other questions before we move back? Anything about what you saw? Like what I want you to, like if you can draw a picture about what GR is, I wanted you to start with this, what the field equations are, right? Which relate here, curvature to our matter content, space-time and matter. And we say that we can build these out of all of these things here. Okay. And if you wanted to work out an actual problem, you'd need a little more. This is all you need intuitively, and these are all the quantities that you'd have to work with. The only thing that you'd have to do in addition to this is work out things for a particular observer. Because if you've noticed, like all of the stuff that I've written down so far don't account for anyone being present, no observers right now. So when you have observers, you have a frame of reference. And if you remember our special relativity course, we need to work out Lorentz transformations. So there are additional things that you need to work out, which are essentially related not now to your, you have to work out like your position vectors, you can work out your tangent vectors, you have to work out your momentum for vectors. So there are quantities related to this that you'd have when you have an observer, but these are all the players that you have. If you have this, you can solve Einstein's field equations, or conversely, if you have a solution to the Einstein field equations, you can do physics. Okay, so today I wanted to show you the covariant derivative. And to do that, I wanted to discuss a topic that I've been wanting to talk about for a long time, and I've told you that it's important. Okay, so does everyone remember our definition for our basis vectors? My basis vector that I had, I said it's defined this way. And I do want you to think about, when you see equations, you should start to at least have a picture about, in your mind about what they mean. Like when I first learned GR, I found it easy to just look at this and say, well, it's the partial derivative of S with respect to X mu. What does that mean? No idea. They're just symbols. I wrote these out. I wrote out the letters. They didn't have meaning. But remember again that if you, in GR and in differential geometry, I'd probably say you're lucky that you can draw pictures, because once we come to QFT and quantum mechanics, you don't have that luxury, not physically at least. So always draw pictures. Always draw pictures if it can help you. And remember, the idea was that if you have a manifold of any kind, if you had a point here and another point nearby, right? In our curve, if I had a curve like this, C, and if you remember, I said it's parametrized by lambda. It means that for every value of lambda, it just is one particular bit of that curve. Okay. And every time you have a particular value of lambda, like for example, C0 would be this point, C1 would be this point, right? That's how this works. And this particular curve, I'd said there's a separation vector between these two nearby points. And I said we can define our basis by taking a separation vector, and I call this S, sorry, ds, it's actually ds. And the separation vector, I'm going to now draw a chart of coordinates here, which would look like this in my local tangent space. And for this red vector that I have here, I'm going to differentiate it by my 3 different coordinates that I've drawn. Like it could be I hat, j hat, right? For example, you also have a direction of time, which I've suppressed. And this thing, whatever this you get at the end of it, is my basis vector. That's how I've defined it. I've looked at my separation and I've asked myself, how does this change if I take a step in this direction, if I take a step in that direction, if I take a step in the time direction? How does the interval between my 2 events change? And whatever that is what I call my basis vector. Okay, and you'll see if any of you are seriously interested in cosmology, you'll find that the coordinate system that you most often want to work in is the polar coordinate. Okay, you'd work into the polar coordinates. If you're working with a particular other area of cosmology, you'd have various things called gauges that you have to work with. So changing coordinates you'd have to learn how to do that fairly easily. Okay, and remember, so if I had this here, how would I introduce a change of coordinates? I'd say that for whatever I have in my manifold, the actual calculations, if you remember our previous discussion, happens in our RD, right? Remember that we said that our point, whatever, is isomorphic locally to RD, which means to say that if I had my separation vector, to me it would look like maybe this, and I'd have my own coordinate system, right? And so if you ask yourself, well, this is Cartesian. If I had a polar set of coordinates, how does this look? How does this look? And so you need a way to translate between these maps. And so if I had a map, if we call the map M, well, going back would just be M inverse, right? What does this mean? It means M is some sort of function where if I take this particular point, I'd say, guys, I have this drawing of my vector here. How does it look in my different set of coordinates? Well, I have to take this point. Let's say it's 2, 1 in my coordinate system. I'd say, well, what's the map 2, 1 in the new coordinate system? And you might have a vector that looks like this here. And that point that we had here might correspond to this point at the tip, right? And how do we go back? Well, we say this thing here, which is my 1, 6. What does it look like in my old map? Well, you take M inverse 1, 6, and you get this. Okay? So you'll notice something, that a change of coordinates, right, is no different from me applying M and M inverse. Can you see that? It's almost like the identity transformation. You have M and M inverse, which means to say if I'm doing nothing, I have M times M inverse. That's for the intuition for it, which is to say, okay, if I have my basis vector here, right, which is defined as what I said earlier, the separation vector and how it changes with my coordinates, you're now asking, how does this change when I move from my Cartesian to my polar coordinates, right? How does this change in this coordinate system? Because I've defined my basis vector in terms of this. How do I write it in terms of this? And from what I've told you here, it's almost like inserting the identity. And the way you do this is I'm going to just take here, I'm writing my separation vector like this, and I'm going to multiply it with, okay, dx nu, which is my nu. I can put a prime there. Can everyone agree this is on, maybe this might confuse you. I'm going to put a prime. Can everyone see the prime? Yeah? Does everyone see this?
Yeah.
Okay, so can everyone agree that this is the identity transformation? This thing here. It's just the same thing divided by itself. It's 1. I'm multiplying 1, which in differential geometry is actually inserting this coordinate system. And then I'll show you how. So this 1, I'm going to write it this way. I'm just going to take the separation vector by dx prime mu this time into, okay, does everyone see it?
Yeah.
Does everyone understand how I've gone from the following to this one? That's all there is. Get this, check this out. So if I had my definition of what the basis vector was, can't I apply that here? Isn't this nothing other than my basis vector? But now I've taken it with respect to my new coordinate system, which means this thing is E prime times should be down. Sorry. Does everyone see this?
Mm-hmm.
So if I write out the full equation now, it means this is E prime mu, is E mu. So I've written out an equation where my old basis vector and new basis vector are related in this way. Does everyone agree? Is there any question? This might be complicated, but if you draw a picture, it should be easy. That I had a separation vector. I've worked out the separation vector in one coordinate system. And if I want to change my set of coordinates, it's nothing other than inserting the identity. And inserting the identity means if I had something like this, if you want to change coordinates to something else, I'm just going to write that something else with a prime. And I'm going to give it a different index. It'll have the same 0 to 3, but I'm not going to use mu again. So one way that you can check that the equation I've written down is still valid is count the index that's free and count the index that's contracted. So note now, I have an x mu at the bottom. I have an x mu at the bottom. Remember our notation, d mu is the same as the index. Yeah. So this actually might be a little confusing, but the idea is if I write d with the index down here, in the denominator, it's actually up here. Conversely, if I write this, it's this way. This is the notation. It might be confusing the first time you look at it, but if you write this down in practice, this will become second nature to you. Okay, so based on this definition here, I want you to look now back at my equation for my basis vector, right? So E mu here on my right-hand side here, it has an index down, right? The left-hand side has an index down. So I'm in agreement so far. The problem I have right now is this new index. I need to be sure that this and this are contracted because then I have an agreement with the left and right hand side. Remember I said that? We need to make sure that the left and right side have the same free indices because if they don't, it's rubbish. The equation's wrong. So if you look on the left hand side now, this is an index down, this is an index up, which means these are contracted. So if I had to write out the full form for the left hand side, okay? If I had to write out the full form for this, it would actually look like this. So I'm going to write the E on the left hand side. Mu equals E prime 0 dx prime 0 by dx mu plus E prime 1 dx prime 1 by dx mu plus da da da. Does everyone agree? So can you still see that this thing that I've written down is actually the same equation? There's actually 4 equations again. Why is it 4? Because I'll have a sum of 4 terms here, but at the same time, I have a choice of index left to me. Mu could be, if I set mu is equal to 0, you'd see that it changes here, I put it in here, and I put it in the 2 remaining terms. Does everyone see? This is incredibly important. Why have I spent so long on the change of coordinates? Because if you remember, one of you complained to me that I said vectors transform the way that vectors do, right? And you said that was a self-defeating plot. It was a tautology. But the idea is that the reason I've told you this is that this change of coordinates is how you define vectors. And I'm going to show you that. So I want you to remember this equation because it's super important. And if you can write this down and practice again, maybe pause the lecture later and come back to it, right? Also for funsies, if you look back at our separation vector here, this equation that I've written in our blue box, okay? Can anyone guess what this is called? The thing that I've now circled in blue, this one. Does anyone know what this is called? Oh, did I make, yeah, sorry, this one. Does anyone know what this is called? So everyone can see, this is my new basis vector. And there's some which accounts for the change in our coordinates, how one coordinate is related to the other, right? It's almost like dy by dx. Does anyone know what this is called? It's called the Jacobian. And now you'll say, oh, I'm familiar with that. I might have studied that before. We don't know what that is. But that helps you understand how coordinate changes are related. So this thing here is the Jacobian. Okay? So if I've written down my basis vector, why is this of fundamental importance? Well, do you remember all of the stuff that we learned about vectors and tensors, right? Were defined independent of basis vectors, but were expressed in terms of basis vectors, which is to say that if I had a vector v, right? How could I write out this vector? I said I could write this out this way. Does everyone remember this? I said the same thing is equal to here. Do you remember this? This is I think the last lecture, 2 lectures ago, I said this is the very important calculation that I'm going to do for you. And we did this out and we proved that if you had 2 vectors dotted with each other, just by expanding this out in the 4 different bases, I did this for you, we arrived at our definition for what our metric was. That's the first thing. And the second important result we got from this was that I proved that the metric tensor raises and lowers indices. You remember? So it's important that you understand how basis vectors change, because how basis vectors change help you understand how tensors change. Any questions so far? Because I'm now going to show you how vectors and tensors transform, because this is important. Okay? So I've shown you this, right? I've shown you how E mu transforms. Do you remember our important equation from the other lecture? Sorry, E mu. Does everyone remember this? I'd written down 4 important equations for you. Do you guys remember this? Any questions so far? This is confusing, tell me now. I don't mind going over this again. This was our defining equation for the dual space, what we call the dual space. And this is the metric tensor. We did this before we discussed outer products. If you're confused, we can go back and revise it. Any questions so far?
Well, can you do that once again? Read the dual space and the metric tensor.
No, I told you, do you remember how we defined our basis vector? We had spoken about our basis vector, and I said this is important because just like how you have your basis vector, you have the contravariant component, this thing here. Remember, we worked this out, and we said they're related, and the way they're related is by equation number 1. And I think you can go back 2 lectures if you're confused, because we spent about an hour on it. So it's important to go through it.
Okay, maybe I will do that, yeah.
Okay, I mean, I could go over it again. We can do that at the end, but I think it's important to go back and revisit it because I think we spent time on it there. So questions that you have, it might get explained when we go through it there. Okay, so the point I wanted to make was that, yeah, so we've just seen how E transforms, right? So if you saw, we found E prime mu, and we said, so E mu could be written in terms of E prime. The equation above here, this one, the one I've written in the box, is E prime mu, then, so it should be here, E prime mu, Tx mu. Right? This is how our, yeah. This is our old basis vector in terms of the new one. But if you remember our metric tensor, which was defined in terms of this, I want you guys to do this as an exercise. You ask for problems. I'm going to show you this. My proof. Okay, proof. I'm going to set exercises. So I'm going to ask you guys to do this. So I want you to take this equation here. Does anyone have any questions about this one? This equation talks about basis vectors. What are basis vectors? I want you to think about them as your I hat and your j hat, right? And relating them to a new coordinate system, which is your r and theta in polar coordinates. Okay, that's what these basis vectors are. And I'm going to call I hat, well, E1. I'm going to call j hat E2, for example. I'm going to call r E prime as a prime switch. Become 1. I'm going to call theta E prime 2. Okay, that's what these are. And I'm asking you, how are these two related? That's the question we're asking. This is given by this equation. Okay, does everyone understand that? I'm relating my basis vectors, I and j hat, to r hat and theta hat, and they're related to each other this way. Okay, I want you to go home and do this exercise. This is homework. Okay, the first thing I'm going to say is we have this law here. So if I have a vector v, right, maybe I can do this for you. And I said v is expressed in terms of some components. These are scalars, like 5. Okay, so in case you've forgotten what basis vectors are, I said I can write a vector v as 5i plus 6j plus 7k, right? What if I call I as x1. I call j as x2. I call k as, sorry, I'm going to say e. What if I call I hat as e1, j as e2, k as e3? Okay. And whatever coefficient is next to e1, what if I call that v1? 6 can be v2, 7 can be v3. So now note that this equation here just says that I can write this out as v0, e0, so v1, e1, v2, e2, plus da da da. Okay? Does everyone see? It's the same thing. This is just I hat, this is 5, this is j hat, this is 6. Right? Everyone sees this? So we're going to do an exercise now, and we're going to say that what if now? Does everyone see? We did this exercise two lectures ago, and we said we can expand it two ways. Right? I can expand it in terms of the dual basis. Yep. Right? What if I now, instead of E, what if I use the change of coordinates here? And let's work that out. So if I had V, my vector, is equal to V mu. And instead of E mu, I now have E prime. I'm just substituting. Can everyone see? Yeah?
Yeah.
Okay. Yeah, so we've got this. And dx mu d, that should be V prime. Okay, wait, I'll work this out in a bit. I don't want to make sure any of you are confused. But the goal is we want to substitute this in here and find what V prime is, meaning my vector expressed in the new set of basis vectors. Okay, we're going to work this out. That should be a prime. Yeah. Okay, we're going to work this out, and we're going to see how this transforms. So essentially, if we know how the basis vector transforms, we should know how the vector itself transforms, because the vector is defined in terms of the basis vectors. And we're going to see that anything with the index down, we'll get a transformation for vectors, and we'll find how this thing here, this v mu, we'll find how they transform. And we'll see that in general, we'll arrive at the following transformation laws. You'd find that any quantity with an index up will have this law. Will have this law. And any quantity with the index down, this could be a vector of any kind, will have the opposite. Yeah, we'll give this to you as, this can be homework. And the way we do this is essentially to substitute the change of basis into our vector expansion. And this thing here is how you can define vectors in GR. And what I mean by that is to say that any quantity that transforms in this way under a change of coordinates is known as a vector. And if you remember earlier, you have something like this, but with tensors are built out of vectors. You guys remember this? I said this, I'm going to introduce new notation. I'm going to have G with a bracket with two things inside it. And I said this thing is defined as, does everyone remember this notation? I'd said, well, G itself is made out of do you remember this? We had our outer product.
Same.
Right? And if I have something in the bracket, it means I'm just going to take dotted with P, dotted with Q. Do you remember? So if you work out that, and you see now, I can ask, how does my metric tensor change with the change of variables? You'd see that the tensor itself follows this rule, that if I have T prime mu nu, okay, it'll be related to the old one in terms of T. T mu nu should be equal to dx prime mu. Put row. Okay, and this is important. If any of you are wondering where we get this from, you can actually derive this yourself from stuff that we've done so far. I've just done the same thing here. And this might be a good way for you guys to revise. So if you have a doubt, we can do this midweek as a problem-solving session. But I'm just going to take this change of basis function, equation, and plug it into my vector expansion. I'm going to go back 2 lectures ago to how I defined the outer product in tensors, and I want you to prove. This is homework to prove this statement, which is the same thing, that we know that tensors, right, are constructed out of basis vectors. They have something to do with basis vectors. And we know how these basis vectors change. And so we're going to combine this to see what this looks like under a change of coordinates. And that's our homework. We're going to prove this. And if you guys remember earlier when I made the statement and you were all upset when I said vectors are things that transform like vectors, tensors are things that transform in tensors, this is the actual mathematical definition. Vectors are quantities that transform this way under change of coordinates. Tensors are things that transform this way under a change of coordinates. That's an alternative way of thinking about them. Okay, so let's move on to the covariant derivative. This is not extremely important for you to derive on your own. You can, because we're going to use this equation again and again and again and again and again through your course of time in physics. I want you to think about it, because the reason I'm not doing this for you now, I started and I erased it, is because I think it's important you sit and work this out, because I actually gave this particular problem. I think, Pugar, I want to hear your voice because I haven't heard from you in a long time.
Yes.
I think you'll remember that I gave you guys, I told you, help me with my conformal field theory homework.
Oh, yes.
And we had something like this. And we had looked at it in terms of Tz and Z bar. You remember?
Mm-hmm. Yep.
Use the very same equation, in fact. So that's the defining equation of tensors along with the outer product. So I could do it for you, but I think it's important you all go back and sit with it, because only if you think about it will you start to understand the stuff. So if you're confused, you can Google basis vectors, you can Google change of coordinates and why are we doing it. You can also rewind to the lecture I'd given you 2 weeks ago, because we covered a majority of what we're doing here. Okay, any questions before we move on to the covariant derivative? The key thing that I wanted to leave you with, the intuition, was this thing here, the picture that we work in the real world, that's our manifold in blue. All the physics that we do in our notebook is actually with a set of coordinates. So I've worked with the coordinate change, and that's equivalent to inserting the identity. Okay, so any coordinates before we move on? Any questions before we move on to what connections are? So can I have a show of hands from anyone? Because when I first saw this E, I was wondering what on earth this is. So is anyone confused by the word basis vector? Does anyone have any questions with it? Because if you understand this, the next bit is easy.
I think we can proceed basis vector. We know what.
Okay, so we're now going to move to connections. And the point of the connection is that we need to understand, remember, how they lie. I told you that 2 tangent spaces on our manifold. And tangent spaces are important because what are tangent spaces? Velocities. You can think about it that way, that the velocity of something here is different from the velocity of something here. We can't compare it. It's in 2 different languages, is the way to think about it. And the change of coordinates is a way to express our physics in a different language. Okay, so we need to compare these 2 vectors. And if you remember what I told you before, the path that you take to compare them is important. Okay, so to compare these 2 things, okay, we need a way to connect this tangent space here to this tangent space, something that connects these 2. Think about it like a translator. Okay, and that is known as the connection. So in GR, okay, scalars are not a problem. If you have a field that returns a scalar value at any point, meaning if you're on this curve and you ask, okay, what's the value? It'll give you a number. And you're here and you ask what it is, it gives you a number. That's okay. It's not a problem because scalars aren't affected by a curved manifold. Okay, so if you had a scalar, the notation for a scalar in GR is something like this. You'd often see it. It's a number. Okay, so a scalar doesn't matter. We're okay. It's just the rate of change is a partial derivative. So this would just be this. Okay. Is anyone scared or confused with this notation? Because remember, how many equations do we have here? 4 equations. Remember, this is 4 equations. It tells you how the scalar changes with time. It tells you how it changes with space.
Chinmaya, you said the scalar doesn't change, right? The scalar doesn't change, but the values the scalar measures changes,
Yeah.
right?
Yeah, fair enough. But the way that it's not dependent on the path. The values will change, sure, but unlike a vector, we can compare the two, which is why the scalars aren't defined in terms of tangent spaces. So we don't need a connection to talk about scalars. Right? They live in the real world. So this law applies that we could just talk about scalars the way we did. Normal differentiation is valid for scalars in GR. Remember the earlier bit that I spoke to you about, that if you want to do derivatives and differentiation in GR, we need an extra piece. The argument is that for scalars, this extra piece vanishes. We can do that again as homework once you see what's coming in the next section. Okay, but for now, the point is that you can work with scalars freely, take partial derivatives, whether you're working in curved space or in normal flat space, it doesn't matter. The problem begins is when we're talking about vectors. Okay, so we need a connection, and I'm going to show you how we relate basis vectors. Right. So remember, if you want to talk about vectors that are associated in one tangent space and a vector that's in another one, okay, to simplify our problem, when we take a vector v and a vector w, we're going to expand this out in terms of the I hat, j hat, k hat. Okay, here's w mu. Bad habit. Yeah, there we go. Right. And now we're going to ask ourselves the question: how did these two relate to each other? How do e mu and I can put a prime? How do they relate to each other? You don't want to put a prime because prime means you're changing coordinates. Okay, so that thing here is known as the connection. And I'm going to define it for you, and we're going to talk about what this is. So do not be scared about scary looking symbols, because GR is full of them. You just have to be comfortable with writing them out. That's the reason I want you guys to do a lot of practice, because writing in indices is important and working with them is important. So here's the connection. So we're asking ourselves, how do the basis vectors change? And the answer is that we take the symbol that we have, right? Our Laplacian symbol, this thing here, our connection, it's written in terms of this Laplacian. And what you're going to do is you're going to write the basis vector down in tiny letters of the original vector you're looking at, okay? EA. And then you're going to ask, apply this thing to, in bigger letters, EB. And in translating what we've just written in notation is asking ourselves, how did the basis vectors change with respect to each other? Okay, you can think of this as the change of the argument, meaning whatever comes to the right, the change of its argument in the direction indicated by the subscript. Okay, we're looking at how EB changes in the direction of EA. Or in other words, you can think about so what is the example? Whenever I'm talking to you about things here, I want you to relate it to I hat, j hat, and k hat, because hopefully those will be old familiar concepts to you. And what we're asking here is whatever this B is, for example, it could be theta hat. How does theta hat change with respect to I hat? Maybe that's a bad example because we're looking at a change of coordinates, but think about it in terms of, draw coordinate systems for you maybe. So you're going to ask yourselves, if this is one set of lines, how does this change if I take a step in another direction? Or if I have this red arrow here, how does that change when I take a step along the blue? Okay, that's what this equation here is asking. Okay, does everyone see it? This is our notation. How does EB change in the direction EA? And the answer is, we're going to say that we're going to write it out this way. Is equal to, now you see our Christoffel symbol that I said. Okay, now this bit is, I want to talk to you about it because the indices are something that it will confuse you, but you have to write it down, because only with writing it out again and working through different problems will you be comfortable writing this out. Okay, so before I write, you can often predict what equations look like in GR. Okay, so the left-hand side, how many equations do I have? Pugal, I'm going to summon you for this answer. Pugal, how many equations on the left-hand side? Where is Pugal? Okay, Pugal is away. Let's take someone who hasn't answered yet. Let's take Rishi. Rishi, can you tell me the left-hand side, what are the free indices that you see?
We have 2.
You have 2, A and B. So you're expecting about 16 equations, right?
Yes.
So, okay, so A and B, they're free indices. Okay, which means I'm going to write this out. If I have A and A here, this is wrong. It's wrong because I have A as a contracted index, right? This is wrong. A has to be free. Whatever I have on the left-hand side that's free has to appear on the right-hand side as free. Okay. The other trick you can do with GR is if you have an index, so this is an example of an equation that's wrong. Okay, I have the same free index on the left and right, but one's at the bottom, one's at the top. Or in other words, one has covariant indices and the other is a contravariant index. So this is wrong. Whatever you have on the left-hand side and the right-hand side has to match. Okay, so this is important because this is intuition that I want you guys to build for GR. So I don't know what's coming yet on the right-hand side. Okay, but what I expect is that A here is down, right? My index A is down, my index B is down. So whatever it is on the right-hand side, I want A and B to appear at the bottom. Okay? And as long as that is satisfied, I can have all kinds of contracted indices around that. Meaning, I could even have some kind of weird equation like this. Let's take some kind of tensor. A, C, R, C, B, T, A. Sorry, not A. T, X, X. So can everyone see this is still a valid equation in terms of indices? Because here I've got one free index A, here I've got a free index B, I've got a repeated index C, but that doesn't matter because it doesn't appear on the left-hand side. I've got another repeated index, but it doesn't matter because it doesn't appear on the left-hand side. Okay? The problem
Those are the dummy indices, right?
Yeah, dummy indices. The problem is that I don't have any quantity that actually really satisfies these criteria. So I can write out all kinds of nonsense equations I want, but if I don't have a quantity that satisfies them, well, yeah, meaningless. Okay, so here's how it works. So whatever it is on the right-hand side, we're expecting A and B to be at the bottom. And the symbol that we use, okay, for this thing is called the Christoffel symbol. A and B come at the bottom. Okay, now what you do is you take the index on the top. I'm going to give it a new name because it's a dummy index. And on the right, I have a basis vector. So can you see this makes sense in terms of indices? I have one contracted index, but it doesn't matter because it's not there on the left. The indices that are there on the left relate to the ones on the right. Okay, and this is a definition. This, so what if you had to read this out, this statement mathematically, what I've said is the basis vector B, EB, right? How it relates to the basis vector EA, how it changes with change in EA is given by this quantity here, whatever this is, times this thing here, which is a new basis vector, right? So there's now a bit of a problem right now. So I want you guys to see, because the physics of this is beautiful, but at the same time, I want you to understand what you're trying to expect and what these kind of quantities are. Okay, so if I write out a vector right now, V is equal to V mu E mu, okay? And I want you to think about this as 5i plus 6j plus 7k, right? This thing here. Okay, E mu is this I, j, and k. Everyone agreed? Okay, what is V mu now? Is V mu a scalar, a vector, or a tensor? What is V mu? You can just relate what I've written and the 5, 6, and 7. What is it?
It's a scalar.
Okay, this is a scalar. Does everyone agree that this is a scalar? Because it's just numbers, right? And you can see because they're contracted. And yeah, these are just numbers. Okay, so you can see the problem. Now, when I look at this definition of my connection up here, right? Now the question, is this a number?
No, it's a tensor.
Okay, interesting. So he said it's a tensor. So the thing here is we need to understand how this thing changes and how it, okay, so why do we say it's a tensor? Because here you can see the indices were contracted. The left-hand side is a vector, this is a vector, and this then must mean that this is a scalar. Okay, or in other words, the actual way that you can tell whether something is a scalar, vector, or a tensor, apart from the example that I gave you, mathematically, we can't use examples as proofs. Mathematically, to understand what a tensor is, what a vector is actually given by this thing here on the left. Here. This thing is how you know what is a vector, what is a tensor, and how it changes. Okay, so we don't know if this thing is a number. I couldn't see who said it's a tensor, but I'm going to mark this out. Yeah. You could think it's a tensor. Why could you think it's a tensor? Well, it's got actually two free indices, which means A and B, you could actually write out values for them, which is, if I had to write this out for you guys, it would be that the basis vector 0, which is actually time, right? E0 is time. And I'm going to ask how let's take Z, changes. This would be equal to whatever this Christoffel symbol is, 0 and Z at the bottom. Okay, C, E, C. But now even here, you can see that this is actually a sum because the index is contracted. So you actually have 0, it would be like this. Right? Does everyone agree? It's and on. Right? That's what this, whenever you see a contracted index, it's actually a lot harder to write down all the individual terms. Okay? So this thing here is what we call a connection. And the answer to what this thing is, this thing here, okay, is actually called a connection. And I think Yuvraj had asked, right? Like, how do you solve the equations to get different solutions to the Einstein equations? One example of this is that a connection, okay, in general, because we have this quantity here, EA and EB, right? In general, it's not equal to EB changing with EA, right? It isn't. There's only one condition under which, of course, it could be 0, but any non-zero contribution, the only way that these two can be equal is very specific. And it says that whatever your space-time manifold is, it should not be twisted like this. Okay, and this sort of twisting is called torsion, like a screw. And if we say that, for example, we require, okay, an assumption we make is that it's torsion-free. What we're actually saying is that these two are equal. And what that means, when you substitute, if you swap the indices A and B in our definition of our connection here, what that essentially tells you is that ABC equals here. That's all. It's just that simple. Okay, so if we work under this assumption, this particular connection is called the Levi-Civita connection. And in the Levi-Civita connection, these quantities here are called Christoffel symbols. Okay, so just to recap, what we did right now is we took basis vectors and we asked how does one change in the direction of another, and we defined the change to be a new basis vector times some sort of coefficient, which we call a Christoffel symbol. Does everyone see that? It's from this equation here. We've said that we've asked how one basis vector changes with respect to another one. And note on the right-hand side, crucially, we've said it is still a basis vector, and it's going to be multiplied by this thing here. And the question to answer currently is that, is it a number? Is it a tensor? What is it? And we'll find that it isn't a tensor, even though it has these indices. It's not a tensor, and the way that we find out it's not a tensor is because when you apply a change of coordinates, okay, this equation does not hold for it. So if you took this T mu nu, for example, and you substituted it with, so you can actually build the transformation laws from this one here, because I've shown you how in general, how an index up changes, how an index down changes. So if you have so let me go back here. So how does something like this change with a change of indices? Well, you just take 1 from the top and you apply 2 from the bottom, which is to say that in general, if you want this to be a tensor. So if I write it as this T ABC, okay, this T ABC, well, it better be equal to dx, dxa by dx. I'm going to say x, y, and z. No, let's take rho, and then lambda sigma. Okay, so only if this equation is satisfied, so now I have to contract. So I have rho, I have that, I have sigma. So only if this equation is satisfied can you say that TABC is a tensor. Okay, and if you substitute this into this one, and you take a change of variables, just to say that you go down to this equation, and instead of E, so that's why I spent a little time on the change of basis vector, formula, because if you know how E prime is related to E, meaning if you change your coordinate system, how are they related to each other, you can calculate everything in GR. Everything. So that's probably the most fundamental equation and useful equation that you have to work with. This one. So it's worth doing this for homework, and I'm going to do that for you. I'm going to give you guys homework, and you can sit and work it out. So if you actually plug this in here, you'll find that this isn't a tensor. You'll find that it has 2 quantities which transform like a tensor, and then there's an additional term there which ruins it. Okay, so this thing is not a tensor. So you can think of it as some sort of coefficients. It's just coefficients. It's like numbers, but they're coefficients. They're not vectors. They don't have any direction. Yeah, you can think of it that way. You can just think of it as some sort of matrix which has some numbers, and when you multiply it in terms of your basis vectors, that gives you the connection. It helps you understand how vectors are related to each other in the tangent space. Okay, that's how you think about them. Any questions so far? I hope this is clear. Like for me, this was a lot of work to try and understand when I first did GR. Okay, so always, okay, when you're working with this, you'll never ever, when you look at any textbook, any paper, wherever you're learning this from, remember we had said this equation is worth writing out again and again and again because it helps you understand where all the symbols should be put up. Okay, you'll almost never see the basis vector written here at the bottom. And always in textbooks, you'll see it written like this. Okay, it's just the same thing. It's just notation that we use. Any questions? So, okay, so we can actually find out, so whatever this is, right? We can already place constraints on what this equation is, which is to say that if I had a scalar, okay, and which went to phi, it better be in agreement with what we studied earlier, which means this should actually be equal to this. Does everyone agree? This is the same law we started with, saying that if we have a scalar, it should transform this way. I've defined a connection, but I've required that if we're working with a scalar, meaning if I change my basis vector to have a scalar here, you can just compare the terms. This is what it is. Or in other words, the Christoffel symbol, yeah, you have to figure out what happens to that. Okay, you can even do the same thing. You can ask what, and I'm going to set this for homework because it teaches you, and I'm going to do this for you maybe in a tutorial because it teaches you important things. So you can even ask yourself how this one is related to this one. Can you guys see? There's a subtle difference between the two, which is I've taken one basis vector and I've asked how does the dual basis vector change in its direction. Okay, and you'll find that if you write this out, it becomes a, so if I had to ask you to predict what you'd see on the right hand side, okay, it'll be the same coefficient that we have. But remember here, can you guys see up here? I want you to look up here at this equation here. Did you see how the left and right hand side, the indices matched? Like I had an A, I had a B, I have an A, I have a B here. How do you think that changes in this equation? I'm teaching you habits that you want to be applying and understand. This is how you understand equations in GR. You can see already that you'd expect one index to be down and you'd expect one index to be up, right? And then what else is missing? Well, you can say I need my right-hand side to also be a basis vector. And how do you complete the picture? You contract the free index. Does everyone agree? And there's actually one crucial detail, which is that if you contract, when you ask how does the basis vector for the dual change with respect to the other one, the normal one, there's actually a minus sign. That's the only additional difference. So these are your connection coefficients, if you would. Okay? And you can actually prove this relation. And I'll show you how. Maybe we can set this out as an exercise, but the way to do this is as follows. If I use this EA, and in here, I have this thing here. Remember, I can take a multiplicity of vectors in the argument. Okay, this, can anyone remember, we did this earlier in the lecture today. Can anyone tell me what this quantity is here?
The Kronecker derivative?
Exactly. So we've got that. And we're going to say this is equal to EA delta BC. Okay? And I'm going to take the condition that B and C are not equal, which means if B is not equal to C, we get of 0, which is 0. Okay, I'm going to take this equal to 0. And this is a fundamental relation you can use. And if you use this, just this equation, I'm going to say this is 3, and you use 1, you can actually derive 2. That's all you need. And you need some clever working with indices. So I'd encourage all of you to try it, because this sort of index manipulation, trust me, if you put in the work to get better at it, when you do GR, you'll fly through the program and you can actually spend more time on research problems and doing things, but you have to become comfortable with doing indices. So we'll work through that, okay? So I'm going to give you some properties of our derivative, and we'll get to that because that'll help you as well. Okay, so if I have my derivative of x1 plus x2, I'll just write out some properties for you. One. This thing, and I'm taking a sum. Okay. How do you read this again? You say, how does y change in the direction x1 plus x2? Right? Does everyone agree? That's how you read it. How does y, the vector y, change in the direction x1 plus x2? And this is simple. This is x1y plus x2 of y. The second thing you can work out is in the direction x, y1 plus y2. I'm going to stop writing the lines, but I'm going to ask you guys to assume that they are still vectors. And you can guess that this is x, y1 plus y2. Okay. What if you had a scalar? Remember, if I have, well, a vector v, which is equal to 5i, I can multiply it by 2, right? If I have a scalar at the bottom, so remember, our scalar notation is this, and y. This is equal to just the scalar out. Okay. And the same applies if the fourth property, that's all we have. X scalar y. Okay, does everyone agree with this? And you can actually use these properties in fun ways. For example, y, you can expand it in terms of this basis. You can also expand it in terms of this basis. And you arrive at that's how we work through things. Okay, so does everyone see this? This expanding a vector in terms of its basis vectors become interesting again and again and again. Okay. So this is the Levi-Civita connection, and that's what I told you about. Now, how do you actually compute these things? So going back, I've defined what the connection is. We're looking at how one changes with respect to the other, and I've said it's actually equal to this thing that I've called a Christoffel symbol, right? So do you guys agree with the following thing, that if the steps that we need to do for GR problem is that if I know if we can calculate this thing here, right? If I know what these things are, I know how my tangent spaces relate to each other, right? Does everyone agree? So I need a way to calculate them, and get ready for probably the ugliest equation in GR. And I'm just going to show you this because you can actually prove it with, I mean, I really don't want to prove it, but you can. I'm just going to write it out for you first, okay? Mu rho. Can I do this from memory? Half G. Then I have a mu, I have an A. Then I have a G. I have an A. V, comma, rho plus G. A rho, comma, V minus G. Rho, comma, A. Okay, that's from memory. Have I got that right? Luckily. Okay. So this thing here, do not be scared, do not be scared, do not be scared, do not be scared. Let me show you what this is. This is your formula to calculate what the Christoffel symbol is. And you can see why GR doing actual work in GR is a problem, because, okay, what do these commas mean? Can everyone see this? There's a comma here. This is just writing this thing here. So wherever you see a comma, it means a derivative. So this thing is this. I'm just writing that for ease of notation. So these are just things that you can work and you can compute these. Like so remember, if we started with, if you know what G mu nu is, okay, you can calculate this. So how do you do it? So here you can input on the left-hand side, you have 4. Out here, you have 4 and 4. 64 equations. You have 64 equations, and you see there's an extra A, which is summed over. It's a contracted index. Okay? So if anyone gave you a metric, which is to say, okay, let's say Apurva is going to study black holes. Okay? You'd start with the black hole metric. This would be a starting point. And from your starting point, what you would do is for every single one of these, how would you do this? You'd find the entire set of 64 Christoffel symbols. Doesn't that sound horrible? Once you've got the 64 Christoffel symbols, from here, you can do calculus. Yay. Why? Because you now have something called a connection. And how do you do it? Let's just finally complete this, because then we're okay. So remember I told you that there's the covariant derivative above, right? Should I actually do this for you? Let's do it together. Okay. So how do you do calculus? The way you do calculus is as follows. If we have, okay, let's take a vector V and calculate the change with respect to mu. Okay, does everyone agree? Does everyone understand what this is? We're now back to our familiar differentiation. Okay, so if we were in non-GR territory, if you were in SR, this would just be this. Sinking. Can everyone still hear me?
Yeah, but the partition for the SR thing is not visible.
Yeah, I don't know why. Yeah, there we go. Okay, this is what it would be. If it was special relativity, it would just be an easy derivative that you could take. But in GR, you have an additional piece, right? And which now hopefully you'll see is this connection. So we're going to do that together now. This is one derivation that I will do with you. Okay, so how do you do this? First step, and you can write this out if you want. We're going to calculate what this covariant derivative looks like. Okay, this is what we want to find out. And if you remember this, I've hidden the basis vector in here because in textbooks they'll also hide it. Okay, so there's a basis vector in there somewhere. And this is defined because often we don't want to write the triangles again and again. I'm just going to call it a capital D. So in general, normal derivative is called this, and covariant is this. It's the same thing. It's a derivative. And you'll probably have, yeah. Okay, this is what this is. So I'm going to write this as d mu. And what I'm going to do is I'm going to expand my vector in terms of its basis. How to do that? Remember, my advice to you is to always have new indices. Do not repeat your index. So can you see here? This would have been very confusing if I had used the same index. Horrible. Absolutely horrible. Okay, this is bad. Never do this because it would, yeah. So we're going to write it this way. Does everyone agree with what I've done? I've just taken my basis vector and written it out as 5i plus 6j plus 7k. Okay. Now what I'm going to do is calculate an explicit expression for what this is. So how do we do that? Okay, this is what we're going to work out. So we're looking for I always get my indices mixed up. Okay, V. Okay. Now, does everyone remember the normal chain rule that we have in differentiation? That if I had to take the derivative of x squared y, for example, right? You'd first apply this Leibniz rule, right? I'm going to do the same thing here. So what would this look like? This would look like this times v mu, and the basis vector doesn't change, plus okay, does everyone follow?
Oh,
Okay, now we just use what we had learned before. So I'm just going to write that out. Remember our rules. So the first thing we're going to use, the first fact, is that the covariant derivative of a scalar is just the normal derivative. Okay. And the second thing we had was that if I have the derivative for this thing here, right? You remember what it is? We had a Christoffel symbol. And you should now expect that the left-hand, right-hand side would be the indices down. Remember? We had a contracted index. You can call that whatever you like. And a new basis vector with that contracted index. Is everyone happy with this formula? This is our definition of what the connection is. And we're just going to use these now. How? The first one, this is our scalar, remember? It's just a number. So this thing can just be equal to d mu v mu, right? And this gets multiplied by plus v mu. And we use the second equation here, which is we need a big Christoffel symbol. Okay, what comes on top?
our compressor.
Okay. Hang on. Yeah. Okay, V. This should be new. We need a new row. Row. Okay, everyone agreed with this? Everyone happy with this equation that I've written down so far?
And sync yet.
Sorry?
I didn't think yet. It is saying that the stuff is without being.
It's still remaining in the Christoph symbol.
Wait, it's not working? Okay.
Yeah, now it's synced.
And now it is.
Let me write that out.
I think you raised
But
it.
it's raised.
Okay, so we got a Christoffel symbol. Can we just read off here? So we had mu and nu, right? So we've got mu, new, new index. Okay. Does everyone agree now?
Mm-hmm.
Okay. We need a way to simplify this further. So this is where, like, I think differentiation is boring, right? Like you can apply it anywhere mindlessly, but I think integration is an art. Like you have to construct the integrals, especially I love contour integration. Like it's amazing choosing different parameterizations. You can come up with interesting and amazing substitutions for your stuff. So integration is an art, right? I think that same thing applies to GR. And you can be really creative with index manipulation. And I think that's an art as well. So I want to point out what we're trying to do here because it's important. So can everyone see that we have some repeated indices? Let's count them first. What is the free index? Our free index from our left-hand side better only be mu. Okay, so you can see on the left-hand side, we've got a repeated index here, right? We've got a repeated index here. And we've got another repeated, maybe should use colors here. Does everyone agree? The only free index is actually sitting here. So what we're going to do is, so I'd actually like to take this common to understand how my equation changes. I'd like to take something common to simplify this further. But the problem I have right now is take a look at this term, right? This is my basis vector here, and this is my basis vector here. Can you see they have different indices? So that bothers me right now because I can't simplify it, but we're in luck. And the bit that we're in luck with is that both the indices here, mu, as well as rho, right? This one and this one are both repeated indices. So when they're repeated indices, we can change them and use that to our advantage because that's just a dummy index. Okay, and here's what we're going to do with that. We're going to try changing it so that this thing here is also mu. Let me just show you and then I'll explain. Sorry, it's new. So I'm going to leave the left-hand side as it is. Okay. Sorry, not the left-hand side, the first term as it is. And now what I'm going to do is just shuffle this around so I use a different set of indices. So I'm going to call the first one V. I'm going to call that rho. Okay. Now we've got a Christoffel symbol. I've got my mu here. And when I had a mu earlier, I'm going to call that rho. So can everyone see? I've just contracted that same index that's earlier. I've just swapped it. And the trick I'm going to do now is I'm going to call this set of dummy index that I have here. I'm going to call that mu. Why can I do this? I can only do this because it's a dummy index. It's already contracted. I'm not changing anything in my equation. I'm just using this smartly. And this is a trick we're going to do in GR. And if you can do this creatively, you're going to find this easy. But for the first time you see it, you might see this is a problem. Okay. So does everyone see what I've done? I've just swapped in. I want you to look here. I've just swapped my dummy variables. What used to be mu, I've brought that to the right. And what used to be rho, I've got it to the left. But it doesn't really matter because at the end of it, it's anyway summed. They're all summed because they're a contracted index or a dummy index. So once I've got that, this might be a confusing step, but I want you to read this and go through it again. It's really an art form that you have the freedom to do this. It's not bad habit right now because you've not done anything fresh. These were already contracted. And I've not changed all four to the same dummy index. I've just swapped what I've called each of them. Which is to say that if I had, for example, if I had the sum here, okay, I've just said instead of this sum, which earlier used to be called rho, I'm going to stop this and I'm just going to call this mu. Okay, that's all we've done. We've swapped the variables. We've not changed anything, but we've done this. It's almost art. And look what this allows us to do. So now when I've swapped this around, look at my basis vectors. And note they're also contracted. And what does this allow me to do? It allows you to take it common.
That's like so the numbers in random addition sort of.
Is everyone happy with what I've done? Is everyone happy with what I've done? I can zoom in if this is a little difficult to read.
Yeah, it's fine.
Okay, so all I've done is I've changed the dummy variable, and in doing so, you can see that I've taken it out common, right? So how does this help me now? It helps me because I can now compare this that I had here. I should now zoom out. Hopefully you've written this down. We can go over this again later. But look what it's allowed me to do. I can now read off what this is back to my definition. Does everyone see? So this thing here is my covariant derivative. So I'm just going to write this out. You can see I still have freedom to rename this index and this index. I can call that whatever I want. These two. Okay, I'm just going to write that out for you. And I'm just going to shuffle it around a little bit. So see, these are just numbers, right? This is a number, this is a symbol, but I can interchange them freely. So just for me to understand that, I'm just going to give you the final definition here. So d mu of v mu. And remember, there's actually a basis vector that's out here. So look here. Can you both see that there's a basis vector here as well as here? So I've taken that. You can think of it as I'm hiding it for now because it's there on both the left-hand side and the right-hand side. So it's independent. My definition is, again, independent of the choice of basis. So we're going to write this as our, right? Does everyone agree? This is my initial derivative, my special relativity normal physics derivative, plus our additional term. What is our additional term? It's v. And we've got mu, which was our free index, rho, and v rho. That's all. I've just taken this equation down here. And this is our definition for the covariant derivative. Okay? Is everyone clear? You can do the same thing. And I want you to, just to see if you've understood this exercise. Okay? For homework, your definition, your practice would be to try and see, because earlier we just did the covariant derivative of a vector, right? I'm going to ask you to go home and do the covariant derivative of a tensor. And all that changes is that we're going to have one additional term in the sum, and you're going to have to do some creative indices to try and understand what the covariant derivative of a tensor is. Okay, I think you can do it. This is practice that all of us have to learn if you want to do GR properly. Does anyone have any questions? We can now do calculus. Okay.
So like what we did by swapping the indices of the covector, the covector and the Christoffel symbol is like basically like reordering the addition sort of, right?
Yeah, it's a dummy index, so you can use the fact that it's a dummy anyway. It doesn't really matter. You can use that to your advantage to just take out a factor common.
Okay.
And this step is really an art. It's a step you're going to do again and again and again. If you want to do research papers or be creative in theoretical physics, it's a trick. It's a beautiful trick. You're going to see it applied in cosmology. You're going to see it applied in GR. And you're going to do, actually, now that I've shown you the trick, I told you that for your homework, you're going to actually show, you can actually use 1 and 3 to prove 2. You're going to use the same trick and prove. I'm going to ask you guys to do this at home. And so I'll set a set of questions for you. The homework should take you some time because you have to think about it and work through it. But if you have any doubts, I'm happy to be around to answer them. So this is how we do calculus. You now have a covariant derivative. Okay. So there's another list of derivatives that you have. I'm just going to write it out without telling you and proving it in great detail, because otherwise you won't have time, because I want to spend the last hour on the Einstein equations. So this is the covariant derivative, which, if you remember, is the derivative of EB in the direction EA. So you can think of it as this. I'm just terrible notation, but you can think of it as this, right? That's what this thing is up here. Sometimes you'll only have, instead of a manifold, right? You'll have a curve like this, and you want to see how the curve changes alongside another curve. Okay, you have that, and this thing is known as the intrinsic derivative. You don't use it all that often. The covariant derivative is more important, but this is a technique you can use if you want to do your own analysis in GR. So just telling you, because you'll see it in a textbook, so it's not too important to learn about it right now. Okay, Why is this important? Because if you understand how to do a derivative along a curve, okay, you'll then take a derivative which is parallel to itself. It's called the autoparallel derivative. And that is the principle of parallel transport. When you take a vector and you transport it along its own like parallel curve, right? The autoparallel equation, that's what we call parallel transport. And that's what guarantees that, we're not going to fight over which path to take because our vector changes. But all of that is based off of this thing here. So if you understand this, the others, how do you actually do that? Well, because here this is just a general vector, right? That we're calculating how does this change. So if instead of a general vector, what if I take its own tangent vector? That's essentially what we're doing. And we're going to say, so this is the derivative with respect to the tangent vector. You'd call this the intrinsic one. I can write that out for you later. And what if we set this to 0? And if we do that, the equation that satisfies that is the autoparallel one, I think. If I'm not wrong, is that the autoparallel? Yeah. Okay. So that's how we work that out. And once you do that, you can calculate GOD6 as well. So that's what all of this is relating to. Okay. So I hope you guys understand what the covariant derivative is, because in GR, remember this. So if you wanted to skip over all the mathematics and just do this blindly, it would be that if you have any problem, so solving anything in GR, right? Remember I told you we want to get to the field equations, which are here. Okay. We start with our metric, G mu. From our metric, we calculate the 64 Christoffel symbols. You're lucky some of them vanish. If you have a particularly good metric, most of them vanish. If you have a terrible space that you're working on, you have to calculate all of them. Once you have this thing here, okay, so now I hope everyone is familiar with what this is. Does anyone not know what our metric is? So far, we've only looked at mildly boring metrics like the Minkowski one. I'm quite excited to show you the remainder. We're going to work on that now. Hopefully, you've all seen what this is. Right? The second one, the Christoffel symbol, you'll now understand how do you calculate it from the metric. It's this ugly thing here. This is how you do your calculations once you have a metric. You can calculate this. There's actually a way to prove that this is the formula for this, and it requires two things. You have to use that thing. The fact that it's torsion-free, and the other fact that you use is something called metric compatibility, which is that metric compatibility is the statement that if I have my covariant derivative, right, and I apply it to my metric tensor, like this, I get 0. And if you use this fact and plug in the equations and blah, 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 and you work with a torsion-free connection, which means AB equals BA, okay, if you work with this and you apply the Leibniz rule, which is the chain rule, right, product rule, yeah, this one that we worked just now, this one. If you do this, you can actually derive this thing here. And I'm not doing it because I don't think it's terribly illuminating. It's just lots of indices and you'll get bogged down by it, but you can prove it this way. Okay, it's possible to do so. Yeah. So does everyone understand how we calculate the Christoffel symbols and what the metric is? Because what's next is trying to understand curvature. And once we have curvature, then you got the field equations. So we've done 2 out of the 4 steps. Does anyone have any questions? No questions? Everyone's happy with what we've seen so far?
I just have one question.
Okay, I can't hear you.
Can you hear me?
Oh, Pugal's back.
Yeah, no, I just left for a while. Sorry. So for the symmetricity in Christoffel symbols, is torsion-free the assumption? Like, is it a physical assumption or is it more of a
it's a physical assumption. I tried explaining this to you earlier, which was that the assumption is that your space-time is not twisty.
Okay.
So yeah, it doesn't twist like this. And in general, you can't have a very twisty, space-time like this, because you'll find that if it's at particular points like this here, you'll find that a particular axiom breaks down, which is that at a point like this, you won't be able to find a locally a neighborhood of points that's isometric to RD, essentially. The tangent space argument that we used. So it's similar to this, that if I had an X, okay, this is not a manifold because around this X, this dot here, no matter how much you try to zoom in and isolate this point, if you're there at this particular point, there's no neighborhood that you can create that's isomorphic to that RD. Okay, so that's the idea, that not all spaces are manifolds. So in general, you can have any kind of weird space, but you'll find that there are lots of constraint equations. Like it may not be a manifold, so it's not worth studying for our purposes. You might have torsion. Yeah, so torsion free has a lot to do with it not twisting, like a screw. So a screw doesn't collapse to that point, but yeah, you have to work with that.
So just one follow-up. When you said twisting, does it have something to do with orientation in the language of
in orientation, that's another requirement. So if you remember, we had spoken about in the beginning that space-time is something, the word is this. Okay? And this here comes from special relativity. And what that means is if you have a curve, for example, it means that at every point in your curve, whatever cone you have, light cone, should be pointing towards the future. So that's what the positive orientation is. So if you have twisting, I've not really worked out, like I'm not an expert on torsion. So you'd have to direct that question. I don't want to give you a wrong answer. But orientation in general in the manifold has, in GR, realizes itself in this light. Okay? So yeah, torsion free physically has to do with your space being like a screw. So we can read more about it, but in the applications, the most important applications that you learn about, like dark matter, cosmology, black holes, in general, we have this Levi-Civita connection. So it's, I mean, for the first interesting problems, it's not really an issue. But if you're studying GR in detail and have a fun problem to work with, yeah, go ahead. You'll have even more equations to solve. Okay, so the question right now we need to work out is what is the curvature tensor and how do we work this out? Okay, and I can start by giving you the definition. So if you remember, the curvature tensor is this huge thing here, right? It's our, there'll be one index up and the other indices down. Okay, this is what this curvature tensor is. And guess how you calculate it? Well, you can see that we started with our metric and we found our Christoffel symbols. So we expect that this curvature tensor, whatever it is, better be derived from the Christoffel symbols, right? So this is the definition for it. And I never memorized this because you can just read it from a book. So you start with this, and you have rho, and you should have mu sigma. Then you have a minus, you have a d sigma, you have a rho, you have a v mu. Okay, so I'll show you, let me just write this out and then we can talk about it. Tau rho v minus tau mu tau rho sigma. Okay, so this ugly thing is our 256 equations here. This is our curvature tensor. And for all the grandeur that we see, this contains all of the information that we have about the curvature. Okay, so now I want to show you what these terms are. So you can actually split this into two and look at this separately. So for the left-hand side, while I write down equations, it's a good check, as usual, to see if the indices on the left-hand side are free and the indices on the right-hand side are also free. So for every term that I write down, you should have the 4 indices that match the left-hand side, both being up and down. And if I have a contracted index, it better be contracted. Right? That tau is here. Okay, so can you say something? We've got derivatives of the Christoffel symbol. Okay, these are derivatives, and we've got products of the Christoffel symbols. This thing that we have is the curvature tensor. It's all there is to it. It's this massive behemoth. And how do you construct it? You find your Christoffel symbols, you can differentiate them, and you can multiply them with each other. But multiplying them with each other is a problem because, so how many equations do we have in this thing alone? So I'm going to write this out for you. You've got tau mu sigma rho tau mu. And here you already you've got another 4, 4, 4, 4. 256, but you've also got one set of contracted indices. Do you see? This is a nightmare. This is a nightmare to actually calculate this yourself. How I'd prefer to do this would be that whether you're working in research or whatever, you better hope someone's worked out this for you so that you could just straight away start. Or you get a computer program and it's a long list of data. So this is why, if you're a physicist, you're also a great data scientist, because the amount of stuff that you have to keep track of is tough, right? So does everyone see this? And how do you actually construct it? So just to break this down and relate this back to your metric tensor, so can you see our Christoffel symbol itself is constructed by our metric? How do you remember that? Okay, so if I had my Christoffel symbol A, B, C, this thing was equal to half G, C sigma, and then I said this was equal to G, A, sigma, B plus G. See, I've done this so many times I've had to memorize it. Minus G, B, and if I've written that right, you'll see that it relates to our earlier definition. So can you see one Christoffel symbol is one term here? Okay, you're gonna find the derivative of this beast. You're gonna find another one here, and you're gonna find two of them, multiply them together, and another one here. Okay, so do you see why this is tremendously difficult to solve? Why is this difficult to solve? Because if you're lucky, we have solutions for it. So when Einstein worked this out, he was surprised that they had exact solutions, because in reality, you have to go backwards. You start with the field equations, and you end up with your solution, which is this. So can you see why, if you actually wanted to sit down and solve the Einstein equations, it would take you a long time. And yeah, maybe it'd be great with index manipulation, and maybe it's a great feeling, but I've not really found the motivation to sit down and work it out myself. I mean, you can in theory, but so now we've got all of this, right? Maybe I shouldn't have erased that, but do you guys remember what the tensor was? What was my fault? Yeah. So there was a Christoffel symbol here, some derivative, another derivative of the Christoffel symbol, and two products. This is our curvature tensor, right? You also have identities for this thing. Once you have this big thing, there are various properties of it. You can go online and Google. They're called the Bianchi identities if you want to work with them, but they're not particularly interesting for us right now. There are various symmetries that this big tensor with 256 equations has, which is that if you interchange two sets of, if you interchange one of these indices like this, you get a minus sign. Okay, if you interchange two, it becomes a plus again. So there are various ways you can use to manipulate the tensor, but essentially tensors aren't scary. So the reason I was trying to tell Pogal that we should get on to understanding tensors through their components, the way they change, and just think about them this way is because in reality, you're spending far too much time on trying to compute the Christoffel symbols and the tensors themselves than honestly to be scared about what they are. They just contain information. They contain information about the curvature, and all the information about the curvature space is in this thing here. And if all of you if you want to calculate this thing, go ahead. The point is that we have often very interesting theories that we want to work on, but doing this is difficult. So I hope you guys see why solving the Einstein equations is difficult, because yeah, it's crazy, right? So from this tensor, do you remember I told you that you have the Vial tensor? So I told you that this big thing here is actually split up into two. Okay, this thing is, from this you can get the Richie tensor, and you can get the Vial. And the Vial tensor is something that's equally large. Like the Vial tensor also has four indices. So if I had to write this out again, another set of 256, but it's related to the ones here. Okay, it's related in terms of taking further derivatives, working through it. Okay, so that's what it is. Whereas the Richie tensor, which we call R mu nu, is important to GR. So I'm not going to write out the Vial tensor because we're going to say it's unimportant for this point in our lives. You may need it if you're working in a specific application, but what I've learned from research is that if everything bothers you, you're going to take forever trying to get through the material. So if you know what's important, you can often discard it and say, you know what, if I work on an interesting problem that I need the curvature tensor, the Vial tensor for, I'll come back to it. Okay, but if you don't necessarily need it right now, you just need to know that you can derive it if you have the Riemann tensor. The Riemann tensor has all the information that you need. The Vial tensor just has to deal with, if I remember clearly, it has something to do with the sphere and the amount that the sphere is compressed. But I don't want to give you a wrong answer. Okay, so for the purposes of the Einstein field equations, we can say the Vial tensor is unimportant, but we can derive the Richie tensor. And the Richie tensor is actually fun to work out. So we've got this huge thing here, right? We had a sigma. Okay, yeah, we started with the rho, mu, sigma, mu. This was our Riemann tensor, right? The 256 equations. How we derive the Richie tensor for the Einstein equations is super simple. I'm just going to set these two equal to each other. And what that means is this behemoth with 256 equations becomes this. Okay, but now you remember that, hey, hang on a minute, we've just contracted one index, which is to say that now tell me how many equations we actually have. What are the free indices?
16 equations.
264.
Okay, so we got 4 here and 4 here. This quantity, this thing here that we have, is the Richie tensor, and it's what's important for GR. Okay, so it's just important that you remember that all the information, if you want it, you can think of the Riemann tensor like a dictionary. It's a dictionary, but if we're working with, maybe for GR, the only thing that's important are a few words from the dictionary, because we don't use all 10,000 or whatever, 60,000 words in the English language, right? So it's there if we want it. If we take what's important, we can see why this is important later, but this is the tensor that's important for us. And this thing is the Richie tensor. And why is it super simple? Because how do you calculate it? Well, you go back to my Riemann tensor here, and wherever you see sigma, set that equal to rho. And you'll see that these two contract. In this equation, you'll have this and this contract, right? And when you work this out, even if you're calculating the Christoffel symbols, once you do that, it'll simplify itself, and we're left with 16 equations from the 256. And that's what's important. And we'll find that even this is symmetric. And this solves 6 more equations. And you can think of this as the trace of Riemann. Okay, so we actually are left with 10 equations here. If you remove this, you're left with 16 minus 6. Okay? And that's what we have. And now, finally, I want you to come back to the Einstein field equations. What I'd written out earlier, okay, was this. I'd written down the G mu nu equals 8 pi G over 3 C power 4. If you restore the factor of C, we usually take this as 1. Okay? Then you have a T mu nu. I haven't told you as yet fully what T mu nu is, but I told you for now, for our purposes, before we go on further, let's spend more time understanding the curvature content, and later you can understand the matter content. So, for example, if you're doing dark matter or cosmology or galaxies and stuff, that's where this bit becomes important. For now, let's just let's take this one problem at a time, and if we can understand what the G mu nu part of things are, you can simplify your life. So someone had asked, how do you work with assumptions? Okay, imagine that you're working in vacuum. You're working far away from a black hole, which is, if I'm here, I'm standing here. Okay, and I'm working in empty space, meaning there's nothing around me. I'm in a vacuum here, and there's actually a big black hole far away. Okay, it's not where I am right now. Okay, so if I say, not even me, if I'm not here, if I'm looking at empty space, okay, you can take the beautiful assumption that T mu nu is 0. So if you're working with vacuum, for example, that's a beautiful simplifying assumption, because then all you have to do is worry about this. And that's essentially what we do with gravitational wave physics, that we see how the waves affect vacuum. And that's one of the assumptions. You'll see for yourself. So flat space is a different assumption. Vacuum is a different assumption. Vacuum is a very helpful assumption because it eliminates the right-hand side. But if you remember what I told you, you can separate this into 3 components, T00, T0i, Tij, which, if you remember, our metric meant that this particular one, these ones, and this entire thing. And they all have their own importance. This is the energy density, this is the stress, and this is the flux of matter. This is just like how you have your curvature content. The matter content is hidden inside the energy momentum tensor. We can come back to it when we need to study applications. But for now, this is our field equation. It governs how the curvature behaves. Okay, so if you have a G mu, okay, it has to satisfy these equations. If you have a G mu, you can't just work in any space-time metric. It has to be one that satisfies this. So if your G mu doesn't satisfy this, it's no good. So it's a constraint on your metric, if you would. And how do you arrive at what this big G is? Well, you could say this. So I'm going to take R mu, okay, and I'm going to substitute half. And just like how I'd set, remember in the big tensor, I'd set rho equal to sigma, right? Which is essentially contracting it. I'm going to take my R mu, and I'm going to raise it. And this thing is called contraction. It's the same thing. I'm just contracting it by changing. I'm going to write it this way. Right? That's what it does. And this is taking the trace. And taking the trace means this is a number. And this number is called the scalar, the Richie scalar. Okay. So I'm going to write that R. It's called R. You can think about it as this, but it's R. Okay. This thing here is G mu. And on the right-hand side, we've got this. Any questions so far? This is the Einstein field equations. This equation shows us that if we know the value of, so what does this actually tell us? Apart from you've read in popular science that, well, curvature and matter are related to each other. The idea is the opposite as well, that if you have the stress energy tensor, if we know what this is, okay, then we automatically know what this is. Okay, so remember the caveat. The caveat is that this only talks about the Richie tensor, not the Vial. And that's the caveat. And even if you know everything about the distribution of matter and all of that, you don't know the Vial tensor. And I told you I'm not an expert on gravity, but from what I remember, this is understood by boundary conditions. Okay, but I've not worked on a project with the Vial tensor so far. And I'm wondering if some of you have heard of this before, but Einstein modified this equation. Okay, and he added a particular constant. But how do you add a constant to an equation? You can't, because if I write out a constant, it's usually written like this, right? The indices don't match. The indices don't match. So even if I wanted to write out a constant, it would have to be like this. And Einstein had added a certain constant to his equation, and this became called the cosmological constant.
Didn't see it again.
Did someone ask a question?
No, Mukund was saying that the.
No, I didn't sync yet.
Okay, so this cosmology, the screen. Oh, sorry. Okay. Yeah, I think it's refreshing now. Okay, the Vial is determined by the boundary conditions. I just said that, yeah, we have a constant that we can add to our Einstein equations, which is the cosmological constant. And if all of you want a phenomenal story with this, you should write this out. And you should Google it, because the story of the Einstein field equations and the cosmological constant is a beautiful story. And the story goes that Einstein had discovered that, or it came to be known that the Einstein equations predict that the universe is expanding. Well,
dark energy.
Yeah, so Einstein thought the universe can't be expanding, it shouldn't be expanding. So he put out a constant which fixes it, meaning it soaks up all of the expansion. And this, we have no answer for what it is right now. And it turned out Einstein had actually added thinking that, the universe isn't expanding. When they discovered that it is, and it was an observational truth, he said it was the greatest mistake of his life adding this term. But today we know it has something to do with dark energy and dark matter. It has to take one value for the entire universe. We don't have a theory for where it comes from. Okay, but it's related to the vacuum expectation value. Or in other words, if you had vacuum, just nothing in it, quantum field theory tells you that vacuum, well, if you think about vacuum in from what we learned in school, you assume it to be empty. It's dark. It has nothing in it. Okay, but quantum field theory tells you that vacuum is the opposite. It's bubbling and swirling with waves that crash into each other. There are all kinds of reactions that happen, and even this vacuum is something that's it's chaotic. And the problem is that to understand what this vacuum is, it's a question in QFT. It's that vacuum itself, which is often described in terms of this way, or take the expectation value of the Hamiltonian in vacuum. That's actually the rigorous, expression for it. You find that there's a non-zero value for it, which means vacuum itself, where it doesn't have any particles or anything in it, does have an energy. So this is actually an open problem in physics today because we've measured that there is an expectation value for vacuum. It's what we call the cosmological constant. It's related to dark energy. And we don't know what it is. And the problem is the value we get. So the actual value is, I forget the units, but it's something like 1. It's very close to 1. Meaning if it was any larger, like we'd be ripped apart and pushed apart. If it was smaller than 1, we'd be sucked in to each other. But the value observationally is close to this, whereas the value we get from quantum field theory is this. And I don't think it takes a physicist or a mathematician to say that there's a huge, huge, huge difference in order of magnitude between 10 to the power 120 and 1. So this is the value that QFT predicts. This is actual observation. And the story of the cosmological constant is super fascinating. I encourage all of you to read it. And in cosmology, we work in a model called the lambda CDM, which means there's a cosmological constant in Einstein's equations, and there's cold dark matter. So it's one of the popular models of dark matter, and we can work through it. But this is the value. The cosmological constant, we have no origin for it. It has to be determined from observation. And given that it's a constant, it takes one value for the entire universe, whereas G mu nu varies from manifold to manifold and from place to place. Okay, so that's what the Einstein field equations are. And I think the cosmological constant is a fantastic story. I recommend all of you to just read. Okay, so I'm going to work through one example, and I think we can take some time to work out black holes as well. Okay, the problem, however, is to do GR. I just want to tell you, caveat. Okay, to do GR, you can't use Newton's laws. They're not relativistic, right? So any computation that you do in GR will be using our metric to calculate all the quantities that we spoke about earlier. But to this, we have to couple an observer or body. Okay, and what does that mean? It means you need to use relativistic notation. From what we studied earlier, hopefully you'll realize that what this means is that you need to start talking about 4 vectors. Okay, and in general, coordinates are not observable, but something I've not covered today, but maybe we can do in the next session if you think you'd like to study this, which is that if you look at calculating the energy momentum tensor, right, you can't do this in terms of just coordinates. You need to define what's called a frame vector. And a frame vector is unique to GR. You won't have seen it anywhere else in physics, and it's something that is physical. Okay, and this is the frame vector, something that you need to calculate, and it's pegged to the observer. So that's something we need to talk about some other time. Okay, you have to work out things called the frame vectors, and once you do this, you can calculate what the energy momentum tensor looks like. Okay, and it's related to quantities that by now should be familiar. You'll work with the 4 vector. You'd have the distance of separation, right? ds squared, which is also x squared, right? It's defined as x squared, meaning it's g mu nu, x mu, x nu. It's the same thing. All 3 mean the same thing. And this changes depending on what object you're talking about. Remember, it's -1 if it's time-like, meaning any object that has mass by causality has to have this length. It's standardized. If it's 0, it means you're talking about light. And if it's space-like separated, it means it's not causally linked. Okay, so it's +1, which means whatever object that you study, This is the first choice you have to make. Are we talking about light? Are we talking about a massive object? Or are we talking about things that are separated with a space-like interval? Okay, and once you have this, you'll find that there's also a momentum flow vector. And Einstein's equation that you see, the famous one, right? It's actually a non-relativistic equation, because you'll see this and you'd say, wait, hang on, there are no four vectors here, so how can this be relativistic? And there's actually a way to write this out in a relativistic form, and you'd see that the equation is actually this, something called the four momentum, okay, is p squared is equal to m squared. This is actually the relativistic equation, where p squared is just like how we had x squared, right? X squared, I don't mean this, but when I have x squared, I mean that I'm contracting the indices together. This is what x squared is, and so similar to p squared is a momentum flow vector. Okay, and if you remember what we'd spoken about with our vectors, our four vector was time and space, right? And you'd find that the position four vector combines energy with momentum. So that's what this is. So this equation here actually tells you that E squared minus the, so you should scroll down. And you actually have factors of C here, which then tells you that, this is what the C form, whatever the factors of dimensions, I haven't worked it out yet. But this is the relativistic energy momentum relation. We can work with this. You'll see often that if you have light, it means that it's massless. And if it's massless, it means the energy better be equal to the momentum squared. So these are various different, say, choices that you work with. Okay, you define this, and once you do, you have frame vectors. Once you do that, you could determine various different quantities, but these are choices that you've got to make. And that's what the doing calculations look like. Okay, so once we've got this out of the way, let's take a few examples of solutions to the Einstein equations. Okay, the first one better be something we've seen before. Minkowski. And I promise you, this is the last time I'm going to talk to you about this, because I think by now you've said, well, come on, we'll only be doing special relativity so far. But the idea is that whatever our Einstein equations are, it better hold for special relativity as well. So this is the first consistency check. So the consistency check for Minkowski is the following conditions. So if you remember our Einstein equations, which were r mu nu minus 1/2 g mu nu r equals 8 by g 3 t mu nu plus a constant. Okay. Often in textbooks, you won't see the constant written out, because let's not confuse each other while we're studying it for the first time. Okay, but Minkowski takes the following assumptions. So you all asked, how do you arrive at different solutions? Here's the assumption from Minkowski. Space is empty. This should now make sense to you. Well, flat space, which means special relativity, not GR, means that there's no curvature. If there's no curvature, it means there must not be any matter content significant enough to cause curvature, which means we're looking at empty space. Okay, that's the first one. And the second one we're looking at is that the cosmological constant vanishes. But for our purposes, we don't need to think about the cosmological constant, so we can come back to it on a separate talk. We can even go into detail about it. Okay, so what do our equations now imply? The equations imply essentially that okay, we've got r mu nu equals 0 is the implication from Minkowski. Okay, and there are many such metrics like this, and you'll find that if you solve this, you'll get our familiar g mu nu. Remember, the g mu nu is the solution to this, which will be this. Okay. Yeah. This solution. So if you actually work this out, and this could be, I wouldn't be cruel to give this to you as homework. Unfortunately, my professor wasn't the same, so he gave it to me as homework. You can actually work backwards from this and calculate your curvature tensor. And you'd find that if you actually work this out, so if you start with this metric now, okay, and plug this metric into our formula for the Christoffel symbols, which by now I should be able to write with memory G sigma b comma c plus g sigma c comma b minus g sigma b c comma. Yeah. So if you work out this, the many different Christoffel symbols, you'll find that they'd vanish. We get zero, meaning flat spaces have connected tangent spaces. Okay, that's one exercise we could do. When we do and find this out, you'd find that the curvature tensor itself is zero. Okay, when you work this out, you could even work backwards and we'll find this to be true. Okay. Okay, so this is what this is. I'm wondering if we have time today to discuss the Penrose diagrams. Otherwise, I think we've done a lot today, so maybe we can discuss Penrose diagrams to you tomorrow or another, sorry, not tomorrow, but the next time. So there are other vacuum solutions. So I wanted to say that if we work in the condition where T mu nu is zero, right? There are other solutions that aren't just Minkowski. And if you're working with gravitational wave physics, there's one that also works like this, which is, if I give you the example, minus dt squared plus dx squared plus t squared mu this is called the plane wave solution. Okay. U is a function of t defined as t minus x. Okay. And this thing is important to gravitational waves. So let's see why. So as you can see, we have, can you see? So here's what's important. You can read off the coefficient of dt to understand how our time behaves, and you can read off the coefficient of our spatial, what do you say, metric components to understand how space behaves. So you can see there's a difference between our normal Minkowski and this. It has the Minkowski signature, right? So it does obey special relativity, but we've got some additional fun functions in front of our y and z. Right? This is a solution to the Einstein equations. You can even constrain it. And if we, so u, this is u, it's here, okay? We say that the functions p and q obey the following equations. There's also a velocity term in here somewhere. You can work out the dimensions. Okay, this is what it obeys. This geometry is a solution to Einstein's equations as well. However, it's a solution under specific circumstances, which is that R mu nu is zero. So it's also an empty space solution. You can see that there's an equivalent statement, which is that p double dot over p. The double dot, remember, is a derivative with respect to time, meaning p dot is defined as dp by dt. Okay? Plus q double dot over q equals zero. They're the same thing, equivalent statements. Okay? This is a very special example of a solution, which is a gravitational wave solution. So this is a very, very simple example for it. We're going to go deep into how we calculate gravitational waves, where it comes from. But usually when you work out gravitational waves, the simplest example is to take empty space, which means we're not near the black hole at all. We're at the receiving end, where wherever our sensors are, we're working in flat space, empty space there. Okay, so that's an example of that. We can look at de Sitter space. We can look at Friedman, Robertson, Walker. That's another interesting one. And we're going to work on this another day. So these are all interesting ones. We could spend one lecture on each. So you would have heard of the Friedman, Robertson, Walker metric. I think I spent one day talking to you about cosmology. Okay, does anyone remember this equation? Just to refresh your memory, I told you that in cosmology, the principle that we work with is that galaxies are on a grid. Okay, and wherever they are now, we're going to assume that no new galaxies form. We're going to assume that no galaxies die. Whatever is in space just
the scaling factor.
Yeah, so I said whatever galaxy is here is going to remain here. Okay, and I said the distance of the square is a. That's the same one that's here. right? Do you remember this? We spoke about this, and we can do a session on cosmology because it's quite interesting, right? So when the box is really tiny, meaning all the grid lines are very close together, all the galaxies are close together, we mean this is the early universe. And when our A is large, it means that we're in the late universe. Okay, so in cosmology, the convention is that A is equal to 1 is today. That's the convention. And as A tends to 0, we go closer and closer to the Big Bang. Okay? And this is a really interesting concept in cosmology. So for those of you who are interested in understanding dark matter and cosmology, this is important. Because what's interesting is depending on your law for the evolution of the universe, how A changes with time dictates whether the universe expands and then crumbles later in the future. Does it continuously expand always? Does it expand really quickly in the beginning, slow down for a bit, and then expand again? All sorts of interesting scenarios. So this is also a solution to the Einstein equations, and something we can study in great detail if you do a course in cosmology. This is the metric that you focus on. Okay, so yeah, that's there. So I think today we can work and just start to talk about the Schwarzschild one. I won't spend more time on it. We'll just look in the beginning. Okay. There's a theorem in physics. Okay, when we start, and I'm only going to tell you this because someone had asked, how do you solve and arrive at a black hole, right? So you can already see why solving the Einstein equations is difficult, because if you start with that R mu nu, trying to arrive at a G mu nu that solves it is very difficult. So earlier it used to be guesswork, and there was no real way to arrive at how you solve it. And then that technique got refined in the future, and there's a way to do it using an action and using the Lagrangian approach as well. It's called the matter variation principle. You can start, and the action that you use to solve the Einstein equations is called the Einstein-Hilbert action. So there's a way you can do that. That's a more advanced course. It's not important right now. Okay, so what are the assumptions that we have with our starting point when we talk about a black hole? Okay, the first assumption is, hang on. Okay. Okay, there's a list of assumptions. Okay. Okay, the first assumption, and this is actually a theorem that you can Google. It's called the Birkhoff theorem. I'm not going to prove it. I'm just going to tell you what it states. The theorem states that we're going to work with on the exterior of the black hole. Okay, we're going to work outside it. We're not going to work in the interior. And the theorem says that any exterior solution where you have spherical symmetry, this last time we have spherical symmetry, we're going to say it's actually stable, meaning G mu nu is not a function of time. Okay, we're going to work with spherical symmetry, which means that any derivatives that you have with respect to that vanish. Zero. You're going to work in a stable metric. And it says that there's only one solution to Einstein's equations that follows the list of assumptions. And that solution is Schwarzschild. So I'm going to start with that today. Okay, and I'm going to show you how we think about it. So this is the Schwarzschild equation, and let's write it first. Squared minus plus. So there's no confusion. D. Let's forget, yeah. Okay, so there's a radial element to this. So I'm just going to focus on, I should write this out properly for you guys. Plus r squared, theta squared plus s squared sine squared, yeah. Right, there we go. Okay. Can everyone see what I've written down? Luckily, we're working with the solution. So this is the equation of a black hole. Okay. And I'm going to explain the various terms that we see. This is a lot of fun. Like, I had a lot of fun when I saw this for the first time. So this is a solution to the Einstein equation. Okay. This is a valid metric. It was discovered by Carl Schwarzschild while he was in the trenches of the First World War. Okay. And I'm going to show you how you read off a metric and what you use to understand it. So we're going to take, I need a volunteer from one of you. Could anyone be a volunteer today?
Okay, I'll try to do.
Okay, Purva. Purva is standing next to a black hole. Okay, and this is our black hole. I'm going to first draw it in a sheet. This is a manifold. So far okay, so this is all I've drawn. Wherever this black hole is, I'm going to label it with X. Okay, the distance between her and the black hole is called R. The mass of our black hole is labeled M. Those are our variables. G is the Newton constant. And I'm going to assume for now that Apurva does not walk around in this way. She has no angular momentum. She's not moving in any direction other than radially. She's only moving this way. Okay. If that's the case, we can ignore this bit of the equation. I'm just going to rub it out because for our understanding, it's not particularly important. It's just the components that are there if you're working in a different setting. Okay. So we're going to work this out together. So my first question to you guys is, when R equals infinity, let's plug that into the equation. So if you use R is equal to infinity, meaning Apurva's far away from the black hole, she's really far away, okay? What happens to our equation here? So if you can substitute infinity into our equation, what does it look like? We're going to have an infinity here. We're going to have an infinity here. So what happens to that term? We have 1 minus 2 over infinity, which means, should write it out here. Okay, so we've got 1 minus 2 mg by infinity, right? Does everyone see this? I need participation because you're looking at a black hole. You guys wanted this, so help me out here.
Okay, the first one will be minus 1 dt square. And then...
So you can see that this term vanishes. And this term vanishes, right? Because it's divided by infinity, which means our metric looks like minus dt squared plus dr squared. Or if I switch from polar coordinates to Cartesian, okay, first important result. What's our important result? When you're far away from the black hole, Minkowski. Everyone clear? We've done this before. Yeah. Is everyone clear with this? We've seen this now. If you're far away from the black hole, it's asymptotically flat. That's the word for it. So GR reduces to SR in this case. Okay, let's go on to interesting cases now. What happens when you get closer and closer to the black hole? Okay. Let's work that out. Let's work on a case. We've seen R is equal to this, it's flat. Let's input R is equal to 4 mg. It's a radius which is equal to that particular value in terms of the mass of the black hole and the gravity. It's a number. You can work out what the number is in terms of solar masses times gravities. Okay, whatever that, it's just a number. So we're going to input R is equal to 4 mg into our equations. What do we get? 1 minus 2 mg by 4 mg plus 1 over 1 minus 2 mg, 4 mg. What happens here? Does everyone
half dt squared.
Okay, so we've got half dt squared.
Then 2 dr.
Okay, so you can see our metric when we get closer and closer to the black hole has changed. Distances are no longer the same, which is to say that in special relativity terms, when we get closer and closer to the black hole, observers don't see events the same way they do in spacetime. This is an important result. It's only unique to GR. You can see how gravity itself affects space and time right now. And by that I mean mass. Mass is affecting the time and the spatial components. Which means if you work out with this particular value of r is equal to 4 mg, let's say it's here, you can start to see that space and time behave in a funny way here. We're now at 4 mg. It's a circle, right? It's a radius. Shouldn't have drawn a square, but it's a circle, right? So around here, space-time starts to behave strangely. Time is starting to slow down. Okay? So we're now going to move to a different example. You can work out the curvature tensor as well with this particular value of r. You can work this out and you can arrive at interesting results. What happens when r is equal to 2 mg? I'm not writing this out. What happens when r is equal to 2 mg? Maybe I should write it out.
We are not able to define it. 0.
Sorry?
0. So it will be
Infinity.
dt
Time
square.
goes to 0, space tends towards some infinite value, right? Nonsense. So remember, so we've got it. This is, I can guarantee this is an exact solution to the Einstein equations, but it predicts that time goes to 0 and space goes to infinity. That makes no sense. And it turns out that this particular value r is equal to 2 mg. This is why I told you change of coordinates is important. We find that if we switch to a different set of coordinates, this becomes what's called a removable singularity. That if you work in a different set of coordinates where not r and theta, but something else, you'll find that it really isn't anything particularly important in terms of that coordinate system. But it does have a physical significance. That r is equal to 2 mg is called the event horizon of the black hole. It means that it's the area where once you cross it, you can't return. And you can prove it through GR as well by looking at the four vector for light, applying that and seeing the geodesic at r is equal to 2 mg. But there's a way to show this classically, which is lazy, is not completely rigorous, but it works for our purposes. So I'm going to show you that in a bit after this, but I want to get to the interesting section first. So can you see at r is equal to 2 mg? We have something strange going on, that the equation tends to 0. The last value I want you guys to look at in this equation is that r is equal to 0. Apurva has now moved past the event horizon and she's standing here. She is at r is equal to 0. Can I substitute that into the equation? What happens? Apurva, you're the one falling in, so you have to tell me what happens at r is equal to 0.
Okay, r is equal to 0.
At r is equal to 0, what happens to our line interval, dr squared?
R is equal to 0. We have the time. No, it's time infinity and.
Yeah, but there's also some other weirdness that's happening, for sure. Like time and space don't make sense anymore, but look at something else that's happening. When r goes closer past this 2 mg, see something interesting that happens. Do you see this negative term here in this line segment, right? When r is smaller than 2 mg, this thing becomes greater than 1, right? Becomes greater than 1, this thing here. What that means is that, can you notice how the negative sign now, our metric has switched. Time now takes on a positive component in our Minkowski space when r gets closer and closer to 0. It's like saying, for example, if it's 1 minus 100,000, we'll have minus 99,000 times minus. So that's plus, right? So can you see how everything that I told you earlier in our special relativity class, that the coefficient around time is important for causality. It can't be a minus. It has to be, it can't be a plus. It has to be a minus. That's why Euclidean space and Minkowski space was differentiated. Can you see that that vanishes when we get close to the center? And the opposite happens here, where you had a plus. Now, this minus term in the denominator wins over the 1. And you now get a minus in your space coefficient. I think it's syncing.
So you mean we get to move to the past of...
Hang on. It's still loading. Should have synced by now. Yeah. Do you see it? So earlier we had a metric that was negative in time, right? It's now switched over. Whatever your convention was initially, we've lost that now. The 1 minus 2 mg over r, the denominator, that becomes negative. So it's switched. Spaces that were space-like are now time-like. Things that were time-like are now space-like. It messes up everything that we know about causality. Okay? And that's the other weirdness, that at r is equal to 0, time goes to infinity, space blows up. There's no meaning of space itself. And the way we describe that diagram is through this. So if our sheet was flat, when we get to r is equal to 2 mg, this is what it starts to look like. Okay, let me draw this better. And there's one particular radius. Remember, it's r is equal to 2 is a radius. So it's actually a circle. I shouldn't have drawn a rectangle. I should have actually drawn a circle. This is what the black hole looks like. Okay, this is at r is equal to infinity. It's flat. When you get closer and closer, you can see you're getting drawn in. This position is your point of no return. It's called the event horizon of a black hole. And this is your singularity, where Einstein's equations break down, where we don't have any meaning to something that's an exact solution of our Einstein equations. So something that's powerful gives us almost exact answers when we use it to understand things that Newton's laws can't. For example, you can use this to calculate anomalous orbits of certain planets like Mercury. It's called the perihelion. You can use it to great accuracy, but it breaks down. And you've seen that for yourself here. And why is this important? Because all of the stuff that we learned about in special relativity comes from the space-time metric. Remember, to start off with, whenever you have distances, it's related to this. Remember, this is your interval. And what did we say in special relativity? We said that we have a Lorentz transformation that preserves this interval. Remember? That this is the thing that's the fundamental symmetry in special relativity. That this is the thing that ensures that, for example, the speed of light is constant. It helps us talk about distances, helps us understand momentum and how they're related. It helps us do a lot of things, this space-time interval. It's the one thing that is unchanged. And that was the fundamental equation of special relativity, that this, that this line interval, the separation between two events is unchanged. But we've seen here that the moment you get anywhere close to this r is equal to 2 mg point, everything that we knew about special relativity and GR, everything breaks down. So that's why it's a scary, scary thing. Mathematically, you've seen it for yourselves now. This is what it is. How can you do fun things with this equation? There are derivations that you can learn from textbooks, which are good examples to learn. I think if I spend time with you, we could do it if you're interested in it. But one thing to look at is orbits. Okay, and this is the talk of orbits around a black hole. And you can ask yourself, well, are there any stable orbits around here? Like, I'm assuming if you threw a ball, or if you we're throwing Apurva. Sorry, Apurva. So if you throw Apurva down here, right, she's going to fall straight in. Is there an orbit that you can go around the black hole? And is there an orbit that's stable? because that's a question you can ask, and it's a fun topic to do as a project. You can see that anything here, if it's unstable, it enters here and you lose. Okay. And there's actually from these very equations, you can arrive at an orbit for light. So whenever I say light, in your minds from now on, you have to take certain properties to be true. For example, p squared is equal to 0, meaning we use our equation p squared is equal to m squared, but light is massless, which means m squared is 0. This is the first equation that you use, and then you know that x squared is also 0, the null vector, right? It's light-like in our cone. So whenever I say light, you have to think about this. And when you apply this to a metric and you work out different things, you can find that there's an orbit which is stable for light, and the value of that stable orbit is at 3 mg/2. And this orbit is called the photon sphere. So if you Google photon sphere, you'll get this is an example of it. You'll find, so this is just an example of how, if you have the metric, you can use it to do interesting things. Something I'd like to do with you is, if we needed a technique to understand these horizons. It's called a horizon because once you cross it, you can't return. What's interesting I can show you a very non-rigorous derivation, but you have to promise me that, you don't tell anyone that I told you this, because it's horribly, horribly non-rigorous, because I'm going to be using classical mechanics to discuss something that's relativistic, and I'd be shot, okay, if I showed you guys this. But if I generally say that you're going to have the velocity. Okay.
I mean, no, we are going to build up the mathematics and then approach it later on. So this would just be an analogy. Go for it. I mean, and on a side note, the lecture is going to YouTube.
Okay. So this is my kinetic energy minus my potential. It's a critical point where I say the potential, gravitational potential for my black hole equals my object's kinetic velocity, meaning my outward force is equal to my inward force. Right, that's what I've done. My kinetic energy equals the potential. So half mv squared equals capital M G over R. So M is the mass of Apurva. Big M is the mass of the black hole. Let's simplify this further. So I can cut out the M's, which means V squared is 2mg over R. V is 2mg over R square root, right? I'd be short if I do this. But what value did we take for the event horizon? The event horizon is R is equal to 2mg. So if you plug that in here, we find that the velocity is root of 2mg, which is 1, right? Which is to say that the velocity I need to overcome the black hole's gravitational potential is 1, which is the speed of light. Now I'm going to quickly erase this before anyone sees it, because it's not a very rigorous calculation that you can do, because I'm combining classical mechanics with GR, but you could do it by calculating the geodesics for light. And if you do that, you find that the escape velocity for light out of a black hole is the speed of light itself. No, sorry, the escape velocity for anything to get out of the horizon is the speed of light. So that's a pretty terrible proof for why you can't escape a black hole. There are more elegant ways to do it.
But even that's possible until the event horizon, right?
Yeah,
even after light entering the event horizon.
So Apurva can happily relax out here. She can happily stay here, but she'd require constantly some acceleration to stay where she is. Okay, the moment she crosses here, you'll find this. I want to do this next time, where there's a good way to think about black holes and the space-time diagrams of black holes, and that way of thinking about it is called a Penrose diagram. Okay. And what you do in a Penrose diagram is, instead of considering space to be finite like this, you compactify it, which is that you take space like this and you treat this to be an infinity, this to be an infinity, this to be a time infinity, this to be an infinite past. So essentially, we're working through this, and you'll see, we'll work out a Penrose diagram, and that's the way you think about black holes. Because once you do that, you can You don't have to draw really large diagrams on Cartesian spaces, but you compactify it such that your infinities are there, and then you can talk about meaningful things. And if you do this, I think I'll do this next time because I want to spend a fresh day on it. But the idea is once you go past this, it's called the event horizon of the black hole. R is equal to 2mg. Nothing can go through it. But it's interesting because the singularity, once you cross that point, isn't a place. It's not a location. It's a time. Okay, and you can see from a Penrose diagram that for any object, whatever object it is, the future is the event horizon, that this always lies in your future, wherever you are. Which is like saying that if I had a light cone, right, which determined my causality, at the top, here, this would be R is equal to 0. Which is to say that whatever object traversed through this, you'd anyway eventually reach the singularity. We'll see this through the Penrose diagram. Yeah. But then this is why you have science fiction. So I think you would have seen something called the Einstein-Rosen bridge, which is someone saying that if you have a flat sheet like this, and you have your black hole that's here, you have your event horizon, and that joins another black hole. And you arrive at another part of the world. So Apurva goes in through here, and Apurva comes out.
Basically a wormhole, right?
Yeah, but it's science fiction because for you to do this, you'd have to cross the speed of light. I mean, the only path that you could take through this is along the x's. So it's fun to see it for the first time, but I don't pay it too close attention. So this is fun. This is a good first look at black holes. And once you have this, because you now have the metric for it, you can calculate the redshift. Okay. And my professor used to tell me that if you want a fun project to do with black holes, you can work on gravitational lensing, which is to say that if I was sitting on Earth, I can set up my own frame vectors. I can work this out, and I could see that if I had looked at a black hole, how do I work around imaging this thing? What does it look like? Okay, so this is something that we can work out. So you'll be surprised to note that not all black holes in real life are Schwarzschild. And the majority of the black holes that you find in real life are Kerr. Okay? And this thing, if you thought that Einstein's equations breaking down past this point was scary, this is a much nicer black hole to look at because it's even stranger and weirder. And it's strange and weird because the Kerr black hole, when you go through it, okay, you don't end up at a singularity. You could cross this point of no return and still not be stuck to that singularity. There are futures which aren't like that. But it's really interesting. There's a future where mass turns negative. And you'll see that the next time we talk about this stuff. So this is your first look at a black hole. This is the equation. You can work out all kinds of fun things by considering this. Okay, so that's an exact solution to the Einstein equations, and you can see clearly here that we get nonsensical results for a space-time metric that is an exact solution. So maybe you guys can figure it out what's happening here. And this is where you'd need quantum gravity. You'd need some description of QFT, which takes this metric and tries to answer what's happening between this area. Okay, any questions for today? I think that's a good place to stop. So just to summarize what we saw today, I want to go back to our flow chart because if you understand this, you understand GR. So here we go. We started with the metric. We can calculate Christoffel symbols for the metric. From the Christoffel symbols, you get this huge behemoth that's the Riemann tensor, which contains derivatives of the Christoffel symbols and products of them, which then means it's a second derivative of the metric and products of the first derivative. From that, you get the field equations. And you can also solve the free field equations and go backwards, imposing certain conditions. And we looked at three examples for it. The first was the Minkowski. The second was the plane wave solution. And we'll go into this in detail later. The third was the Friedmann-Robertson-Walker metric. And the last was the black hole equation. So any questions? Any questions?